Hello, good afternoon. It is time to start this meeting, and it is my pleasure to welcome all of you in this ancient building and this beautiful venue. As you can see, there are the frescoes of the 16th century, which illustrates the history of Ulysses. And this room is called the Hall of Ulysses. And also in this room nearby, there are also other histories related to Ulysses. And Ulysses means the discovery, the voluntary discovery of something new. And this is the reason why the Academy of Sciences, since more than 3 centuries, is hosted in this building. So it is my pleasure to introduce this meeting, which is called Entropy, Complexity, and Spatial Dynamics, with a question, the rebirth of theory. And this meeting is following the publication of this huge volume, which has the same title, Entropy, Complexity, and Spatial Dynamics. So it is a very complex problem, and I know that you will discuss for this afternoon until the evening, 6:30 in the afternoon. So I'm very sorry for not being here with you for the afternoon and the evening, but again, I wish you a beautiful stay in Bologna and a fruitful work here in this room. And I thank Professor Scazzieri and Professor Reggiani for having organized this meeting, and I leave the chair to them. Thank you. Bye-bye.
I just take this opportunity for thanking, in fact, Professor Bolondi, that is the president of the Bologna Academy, and Professor Paolo Monari, that is not here, that is the president of Class of Moral Sciences, for thanking them for giving this opportunity, this beautiful room, this opportunity of changing ideas and reflection also on the future, not only on the present. And then I would like to thank Armando Bazzani from CAST, Professor Armando Bazzani, because his great support was essential in this regard. And I would like to thank the 3 main speakers, Professor Alan Wilson, I hope he's connected, and Professor Mike Batty and Professor Peter Nycombe that are present, because one is the father of entropy, the second one is the father of complexity, and the third one, Peter, is the father of spatial dynamics. So I'm very happy to have them here, both online and physically, and I'm looking forward of environment or this environment or new research direction and new discussion. So now the chair is Professor Mirko degli Esposti, and you will tell us how to proceed. Thank you.
Oh, thank you very much. First of all, as a member of it's a wonderful academy, let me thank, probably not in the right order, but first of all, I would like to thank our guest, in particular the international guest, to be here in present or remotely, and I thank them to be here. Let me thank Professor Bolondi as the president of the Academy for this, for hosting this very interesting afternoon. And last but not the least, I want to just thank Aura, Professor Reggiani, and then I want to thank her and all the organizing of that. And as a mathematical physics interested in complex dynamical system, especially in the urban area, as interested in a complex urban system, I'm really excited about the meeting today, about entropy, complexity, and spatial dynamics. And I don't want to take more time. I think it's time to move on. I just want to mention that I'm very happy to see here people coming from different areas, as it is supposed to be for attacking this kind of problem. So of course, from the Department of Statistics, from economy, political science, mathematics, and physics. And I think this is not only beautiful, but it is also necessary for attacking this kind of problem. And I had the pleasure also to read through the Handbook of Entropy, Complexity, and Spatial Dynamics. And I would like to just to say that for every young student or researcher aimed to apply the mathematical physics technique to complex urban system, this book, it's really a gold mine, and I really suggest to read it and go through the go through the contribution, because you really can capture a long story of research, which is in front of it a very, very promising and exciting direction to follow in order to understand how complex phenomena happening in our urban system behaves. And I think if our now it's agreed, we should start with, I would like that Professor Aura Reggiani presented the workshop, and then we are going through the next. First of all, we will have a presentation of the workshop, and then we will have the first section 1, which will be a discussion on entropy with Professor Sir Alan Wilson. From now on, I would like to thank all the people here. I also see people from computer science, people from some area that probably I forgot to mention, but this is very exciting to have all that are united here to talk about this. So please, Aura, if you would like to talk about your contribution, I leave you the place. Thank you very much.
Okay, thank you, Mirko. So he's also I to thank him because his support is essential. And I would like to start with a sort of background, why this book? And then my colleagues, Laurie, Danny unfortunately cannot attend, but Laurie, Roberto Patuelli, and Roberto Scazzieri, that is an author, will continue with new challenges. Okay, so the idea started a few years ago, several years ago, because we started with some conferences, with some special sessions devoted to understand the relevance of theory models in this era of economic evolution, socio-economic evolution, that can have not always a regular pattern, but we can have unstable phenomena, as we saw recently also with COVID. And then we are entering in an era of spatial economic complexity and uncertainty. So how to map out to deal with this? And I start just, my presentation will be very short, and I start just with this sentence by Krugman. In fact, he says complex spatial dynamics may trigger a series of intriguing growth processes. So already in 1991, the Nobel Prize Professor Paul Krugman had the idea of this intriguing, so also the instability, uncertainty of this logistic curve evolution that you see very regular, but this logistic curve can be chaotic, and what about when you have a multi-layer network, so the dynamics is completely probably not so clear. And Krugman wrote complex spatial dynamics. So then we have to put attention to the concept of space. What is space? Because several persons, also students, ask me, what is Prof spatial dynamics? And then I would like to go back to Alan Pratt, University of Berkeley, in his presidential address of the Regional Science Association meeting, University of Berkeley. He was saying, to speak about spatial structure is to speak about behavioral rule. So in a way, he's joining the social structuring processes with the structuring of space. And then we have also the definition by Professor Nijkamp, Tijkats, can pronounce, space is not only a passive attribute, it plays an active role by determining industrial location, commuting patterns, accessibility, connectivities of cities, and then transport and migration flows. So 39 years, so because we are in 2023, after Alan Pratt, the main question is how to deal with this evolution of interaction and integration between the spatial network structure and the human activities. And what about equilibrium? Stable, unstable equilibrium, how also to understand the different kind of unstable equilibrium. And which is, in a way, the most interesting spatial scale. And here I refer to Professor Michael Storper, who defined this concept of city region as integration, interrelation between the city component and the regional component. And Michael is asking, why do city region grow? Why do some decline? What are the principal regularities or irregularities in urban and regional growth? As I said, which are the events on processes that also can influence in a dramatic way the development of cities and regions. And again, Michael says, okay, in this respect, urban and regional development is a noisy and complex phenomenon. So then we start also to think about complexity and about equilibrium. And mostly explaining the growth and change of region is one of the great challenges for social science that cannot be understood through the tools of a single discipline. So we need a multidisciplinary perspective from all viewpoints, theory, analytical framework, modeling. So Michael Storper and also each of us, that's the reason why we are in this beautiful environment at the Academy of Science of Bologna. So is thinking about multidisciplinary perspective, and I would like to say also multidimensional perspective. And so our idea of myself and my co-author was to identify as main important concept the three main concepts of entropy, complexity, and spatial dynamics, and to look at the interrelation. Of course, it's a long process, so this is just one book, but it's just the starting point. And why entropy? Why entropy? Okay, then we refer here to the father of entropy in our field, that is Professor Sir Alan Wilson. And entropy is the macro distribution for micro-level interaction in a spatial economic system, from which a spatial interaction model can emerge at the equilibrium. And entropy is also linked to spatial interaction, to gravity models, to logic models, to rank size rule. And so the main question is, can entropy be considered as universal principle? So it's not only a measure of interactivity, but also of diversity. So that's is embracing a lot of concepts. And why complexity? So complexity, we can start from the Nobel Prize in Economics, Simon, who already in 1962 defined complexity as the large number of parts that interact in a simple way. And then we have Casti defining static and dynamic complexity. And then in the 2007, we can refer to Barabasi talking about complexity networks, so universal properties, again in complex network topologies. And here we refer to the father of complexity. I'm very happy also that Professor Batti is here, about complexity and entropy, paper in 1974, in which Professor Batti considered entropy as a measure of complexity, spatial entropy as a measure of complexity. And here the research question, of course, is complexity versus simplicity. So are our real-world complex systems guided by very simple rules? For example, we'll see in the presentation by Batti, the power law rule in both infrastructure of Barabasi and rank size rule. And why spatial dynamics? That is the third concept in our book. And here I refer to Liosatos and Isaac, in which they define this paper from the 80s, spatial dynamics as the study of spatio-temporal dimension of socioeconomic activities. And then we can refer already to Adam Smith, the economist in the 18th century, in which the role of region and city and their function was highlighted, and also Mills in his handbook of region and urban economics. And then we go back to Simon and Isaac, who emphasize the spatial organization of cities, and also the hierarchy, the relevance of hierarchy of cities within regions, and so the connectivity in a way. And then I refer to the father of spatial dynamics, that is Professor Naika, who emphasized the necessity to explain dynamic processes in cities and regions. And now we go back to Anderson. If you can remember Anderson in his article in 2008, he was a big worried about the evolution of big data and asking, could big data be the end of theory? So this was the starting in a way of our book to look at which point are we. And then in fact, we are just by means of this workshop, trying to explore if the old challenges has been solved or still there, or maybe we started some challenges, methodological, empirical, and then are still there, or if there are new challenges that can help us in going on with this in this research direction. So we have to go ahead and okay, this was, as I said, is the starting point. And then I would like to leave the floor to my second co-author, that is Professor Schintler from George Mason University, that she will talk about also new challenges, and then to Roberto Patuelli, and then to Roberto Scazzieri. And thank you. So.
Thank you very much, Ora, for that introduction. Let me go ahead and share my PowerPoint. All right, so what I would like to highlight here are new and old challenges. And can everybody hear me okay? Yes. What I would like to highlight are new and old challenges and opportunities in relation to entropy, complexity, and spatial dynamics, and is highlighted in the handbook and beyond. But before we get to that, what I want to do is go back to this paper by Warren Weaver, 1948, because it really sets the stage for the kinds of things that were covered in this handbook. So he delineated between three types of problems: disorganized complexity, organized simplicity, and organized complexity. And he pointed out that in the next 50 years that we would have to learn to deal with problems of organized complexity. So disorganized complexity systems have a high number of interacting components, but still exhibit some degree of order or pattern. And he pointed out that there are basically two approaches to getting at this. One is that we need to exploit new types of electronic computing devices, he called them. And the second is we need to exploit mixed team approaches, for example, interdisciplinary collaborations. Arguably, now we are here 70 years later. So what are we seeing? Arguably, we are in a new era of complexity, as Ora alluded to. And in this context, there are novel opportunities and challenges. So just quickly, the world is becoming exponentially complex, even as Warren Weaver anticipated. Our contemporary world is facing rather drastic geodemographic, technological, and environmental transformations. Cities are becoming more complex as they evolve. The sheer scale and scope of global interconnectedness has become increasingly evident in every sphere. And we have new technologies here that are part of the fourth industrial revolution that are blurring the lines between physical, digital, and biological spheres. On top of this, the frequency, intensity, and complexity of extreme events have increased in years, and this creates, as Ora mentioned, uncertainty and dramatic change at all socioeconomic levels and scales. Of course, the pandemic is just the most recent example. Not surprisingly, then, we see that there is a growing area of interest in understanding the resilience of complex spatial systems. Of particular interest here is how such systems react and respond to shocks of various types, how we can intervene to manage such disruptions, and what the role of complexity and entropy is in these regards. Some of the contributions of the handbook that get at this, I'll just highlight a few. One, there is a need to develop new indicators of resilience that go beyond equilibrium estimates to acknowledge the dynamics of these systems. We can also exploit the hierarchical structure of complex spatial systems, as Czamanski pointed out. And what about entropy? So entropy can play an important role in all of this. For example, entropy provides a lens by which the effects of policy interventions on complex systems can be understood, especially in systems that are unpredictable, vulnerable to shocks, and out of equilibrium. And I like this idea that was suggested by Alan Wilson, that we can think about these systems as planners, basically, as part of a human brain there. And much like the human brain, we can minimize free energy, which is the equivalent of maximizing entropy. And that can allow us to avoid negative phase transitions in such systems. Big data and computational potentialities are here. So we're dealing with a much more complex landscape in terms of the data and the technologies, computational tools that we have in front of us. The computational tools and data at our disposal have become increasingly complex. And in this regard, we have new opportunities, many ways that we can exploit these new developments here. We see new directions in the modeling and simulation of complex spatial systems and new and expanding sources of spatial geotemporal big data. And some of the opportunities here in front of us, for example, these tools and data allow us to capture how micro-level interaction and behavior in such systems give rise to complex structural properties and aggregate dynamics. We can also use such data as tend to have a very fine level of spatial and temporal resolution to understand urban systems at different scales and hierarchies. It also allows us to revisit classical theories, to test them and maybe build on and advance or even contradict these theories. In all of this, context matters here. One of the issues with data-driven tools like AI is that you can run into the problem of overfitting, where an AI computational tool overlearns a complex system, overlearns the details of that system. And this is a problem because while we have these common properties across different kinds of spatial systems, every spatial system has its own nuances and dynamics, which we need to capture. AI can lead to the problem of transfer context bias. So we take an AI system to learn about a particular complex system, we try and transfer it to another system and doesn't work well. Compounding matters is that such tools tend to be black box. We have really new techniques that are coming out right now, including platforms like ChatGPT, generative AI and large language modeling. We may possibly exploit these tools to address these challenges. And we can also think about things like transfer learning as a way of generalizing from one system to another. Next, as Aura pointed out, interdisciplinary perspectives are essential. Again, coming back to relating this back to Weaver here. Exploiting theories, concepts, models, and methods from diverse disciplinary perspectives, including those outside of the field of spatial economics, can significantly improve our ability to understand and model complex systems. For example, we have issues here related to resilience, and we can see across different scholarly domains and applications, we have different definitions of resilience, which creates all sorts of problems related to conceptual, methodological, and operational issues and challenges. Interdisciplinary views and approaches are more than imperative in the new era of complexity, and we can even think about exploiting what's going on in the universe. This is the grandest complex spatial system we can think of. What are the parallels there? What can we learn? What about theory? So that's one of the main themes of this handbook. I would like to pick up on the point that Aura alluded to and what Anderson had the issues that Anderson had raised. Does big data and data-driven approaches to understanding and modeling complex systems render theory obsolete? There is a a number of people who say, yes, there are serious concerns that big data may signal an end of theory. It encourages a shift from the conventional hypothesis-driven scientific method to the use of data-driven techniques that seek to uncover patterns and correlations in the absence of any guiding hypotheses. Another issue here, big data is viewed as an approach where the numbers speak for themselves, or where raw data replaces modeling altogether. Hence, big data research has been criticized for its strong reliance on supporting inductive reasoning. On the other hand, and this is my personal belief, I don't think that big data is really an end of theory, and it can help us in a number of ways to understand complex spatial systems and to develop and advance theories in this area. I started out with a point raised by Wilson, Sir Alan Wilson. An argument is sometimes made that the analysis of data will somehow render modeling and theory obsolete. In fact, the opposite remains the case. We need to understand those systems in the first place to understand exactly what data should be used to better understand them. Big data can also play a pivotal role in bridging geographic and descriptive seeking and nomothetic law-seeking research activities, and move from simple hypotheses here to complex postulates and theories. And finally, I will point out that this idea of big data really isn't new, and we can go into the field of social physics and decades ago, where scholars such as Zip, Stewart, and Warrants were using what would be considered big data at the time to understand spatial systems. And in the process, we saw new geographic and complexity theories evolve. And to steal some language from Alan Wilson, we can think of big data and related data-driven tools as just another tool in our toolkit. Finally, regarding theory, there is a renewed interest in developing a unifying framework for characterizing modeling spatial interaction and dynamics in urban and regional systems. Could entropy be the connective glue here? That leads us to the main research questions of this handbook, and just to quickly highlight them, or as already alluded to some of these. What is the current state of research and knowledge on complexity and spatial dynamics, and what is the role of entropy in this regard? Are there conceptual, theoretical, methodological advances complementary to an alternative to entropy that can provide new insights about these systems? Can entropy be considered the universal principle that enables us to join probabilistic approaches with behavioral approaches to model, predict, and understand complex spatial systems? And two more questions. How can we harness new sources of data and computational tools to understand and model the role of entropy in complex spatial systems? How can we address the issues and challenges? Again, let's about these new tools that are coming on the horizon right now and how we can exploit them in this regard. And finally, all of this coming back to Weaver, how can we foster a mixed team approach, that is interdisciplinary collaboration, to advance theoretical frontiers in this domain? And this tag cloud here, which was based on the contents of the handbook, it basically encapsulates everything that I've discussed and highlighted here. And you can see that at the center of this word cloud, we have the word of entropy. Thank you very much.
Thank you, Laurie. I think the next one is Daniel or Roberto. Thank you. I think if you mind, I thank you, Laurie. I think we can collect all the questions at the end, but I do believe that big data is not going to kill the need of model and theory. Actually, can only be some kind of motivation and help us to go even deeper. Thank you very much. So I think we can leave the questions for the end of this section. Please, Roberto, it's your turn.
Okay, thank you. Good evening, everyone. I'm the kind of the junior member of this of the Editor group. So I'm maybe because of that, I have a more narrow task in my hands. I would like to give you a little bit, because you have received a flyer for the book, but those of you that don't actually own the book, don't know exactly the contents of I can give you a little bit of an overview. So as you can have understood from the introduction, the book is divided in 3 main sections. So part A is about entropy, space, and complexity. So you can see there is a contribution by Sarah Wilson and other important scholars like Barclay Rosser, Ginesta Bianconi, Eleanor is with us, Mike Betty. Part B is about complexity. So this is another pretty big part of the book with John Parr and Denis Poumen, who's also connected, other prestigious scholars. And finally, there is another part C about complexity and resilience of economic systems. Actually, this is probably the larger part of the book with more contributions. As someone mentioned earlier, it's a thick book, right? So lots of contributions. Alan Murray and other prestigious scholars also here. And finally, the part D is about spatial dynamics. Maybe this is a little bit more applied compared to the initial part of the book, which has also more theoretical contributions. So for myself, being maybe more comfortable with the spatial dynamics part of the book, I thought I would focus on this part of the book, picking up some of the, let's say, underlying theme of part D of the spatial dynamics part of the book. So focusing in particular on this part, the main, thin red line that unites probably about half of the chapters in the spatial dynamics part of the book is the role of networks. If you look at the composition of the spatial dynamics part of the book, networks play an important role in several of the of the chapters. So it's something on which it is due to have as more reflection. Networks, of course, can be many different types, right? You can have mobility networks, is something I'm working on in this part of my career. Information network, migration network, commuting networks, all of these are mentioned in different chapters, for example, part D. So these networks, it's not enough anymore to look at, let's say, spatial distribution of economic activity or, let's say the localized value of a geocoded variables, but networks and flows of information and people, freights, if we're talking about goods, if we're talking about trade, are now central for understanding urban and spatial dynamics. This is my interpretation of this. Of course, there is a lot of literature on networks in many fields, from physics to economics, and many tools that have been developed in the recent decades. If many of us are probably familiar with social network analysis and all the implications of that. So new tools have been developed starting from very simple indicators, very simple indices, and now also more complex, let's say, network representations are used, like weighted networks, where in addition to connections, we also have the weight of the importance of these connections that give us one more dimension of the role of networks. So now weighted network measures that have been adapted from the topological networks to be used in weighted networks are commonly accepted, commonly used. You can see a review in the handbook. But how do we move forward from this? From just, okay, now we have weighted networks, but we can have many different forms of network. What if we have multi-layer networks in which we represent different types of personal mobility, of different subsets of the population, or mobility of the population on different modes of transport that, of course, also interrelate, so the networks are overlapped and they communicate with each other. So how can we represent different, well, here I say mobility patterns, but of course it could be other types of flows by mode, by characteristics. You can see another review about this in the handbook. How can we reconcile these different demand networks theoretically and empirically? These are two different separate challenges, if you want, both gigantic, one from the computational point of view, the other from the analytical point of view. How can we reconcile these networks? What makes sense to do and to use in analyzing such complex networks, not in the basic, say, terminology of complex networks, but complex networks that have this level of complexity, different layers, different weights are given to the different to move flows on the same network. Can we use entropy concepts and measurements to analyze these networks, to interpret these networks? So can we reconcile entropy and networks? Okay. And picking up also where Laurie, who was my boss during my master's, so always nice to see Laurie, left off, can we use big data in the analysis of network? We can use, of course, big data now also to verify established theories. There is something about this in the handbook as well, but we can also use to explore new phenomena, right? So for example, mobility data coming from cell phone information. I remember Peter in the past has used cell phone data maybe 10, 15 years ago now in several works. Now probably one of the most precious and hard to find data. Actually, one of the chapters in the handbook starts by saying that now, because of the growing availability of this data, it's possible to explore these avenues. My view is a little bit different, that it's not so easy to get access to this kind of data. Often they are very costly, if you want, and very costly also from the administrative point of view of signing agreements to get access to this kind of data. They are very costly to analyze because the amount of data is enormous. So you need very, very good capabilities in filtering and cleaning the data. And so difficulties in obtaining this data, which could be, of course, very useful, in my view, are somehow slowing us down, right, in gaining new knowledge and developing new analytics for urban dynamics. So maybe one final reflection is, how can we, and Laurie was saying something very similar, how can we improve access to data such as this, such as mobile phone networks, for example, or how can we generate similar data from other sources that can substitute for this data that are sometimes very costly or difficult to get your hands on? So that here in the role of networks in urban dynamics, there are a lot of open questions in my view that can be addressed and will be addressed, of course, in the next years, over which I hope the book contributes and gives you and the readers new ideas, new starting points, right? Because as I wrote in the beginning of the slide, the handbook is a starting point for discussion and for reviving a discussion on also established theories. Good. I'd say this is all for me.
Thank you. Thank you, Roberto. Thank you a lot for this second contribution to the presentation of the workshop around the volume. Can you hear me? Yes. Let me ask first of all if there are. Oh, yes. I'm sorry. Ecco, io lo sapevo, ma hai detto che I have to apologize as a last-minute chairman. I made a terrible mistake. I apologize to our guests. I thought you were talking next. And so I'm grateful to, and I'm still apologize to give a speech for the third contribution on this first section to Professor Roberto Scazzieri, which is another author, and from University of Bologna and Clare Hall, Cambridge, UK. And thank you again, and sorry again for, I thought you were going to talk next. Thank you.
Just a short.
Please, no, even take your time. I mean, wonderful.
Yes, perhaps. Grazie.
Sì, Wilson c'è.
Okay.
Wilson c'è.
Okay.
No, ho capito male io.
Ok, e poi muovo questo. Okay, well, thank you very much. Well, basically, I'm only an author in this handbook. I was not an editor, and I'm still grateful for the co-editors for their kindness in inviting me to contribute a paper which was, as I think they expected to be, a theoretical paper. I have tried to build this set of reflections, of course, on the basis, and I think you should not be surprised of what my contribution in that book is, but trying to think how to build on that set of reflections jointly with the set of reflections coming from the other contributions in the book in order to be able in a way to contribute to what is a very important research question arising, hopefully, from this workshop, of which I've been one of the co-organizers with Pierre at the Academy, with our colleague fellow of the Academy, our Reggiani, namely essentially which way forward. That's why the title, I picked up this title, Complex Systems as a way out of the age-old conundrum between structural determination and contingency. Well, I start by outlining what, in my view, is perhaps a hidden but quite important distinction in the theory of complex organized networks between the positional view and the interactionist view. I will focus, following on the premises already outlined by various authors. One of them was also quoted by Laurie Schintler a few minutes ago, namely Weaver, on the emphasis being on organized complexity and their dominant relevance when studying socioeconomic systems. Then I will very briefly refer to a concept which of course is built on existing and even classical theory of organized complexity. May I just recall Herbert Simon's notion of stable intermediate forms, but which I basically developed quite a couple of decades ago with my colleagues Michael Landerman from Vienna, which is the concept of relative structural invariance, which, by the way, Laurie was kind enough to refer to in her paper. Then, of course, this is just a brief set of reflections. I will, in a way, concentrate my attention to production networks, which have been one of the most important fields of my own research, dealing with production networks as a possible template for the study of organized complexity in socioeconomic systems. In this case of production networks, what is central is the distribution of invariances, of course, in relation with the principle of relative structural invariance, because the distribution of invariances become a very important conditioning element for the evolution of a dynamic trajectory of a complex organized network. And at this point, coming to grips with the concept of uncertainty, I think it would be quite important to make use of Lotfi-Zadeh's concept of possibility as distinct from the concept of probability. There is a link between the role of relative invariances and the role of possibility vis-a-vis probability. And what comes out of all this is that what we need is a way of combining, in a way, and making contemporary use of principle of structural determination, which of course is a limited structural determination, coming out of relative structural invariance and the unavoidable role of contingency. So just very quickly, the two research tracks, positional view versus interactionist view. Why positional view? Well, the positional view is essentially an approach which gives attention primarily to the way in which different elements in a complex organized network are positioned relative to one another across a multi-level arrangement of subsystems within systems. The interactionist view, well, it is of course complementary, but it provides a different perspective, because in the interactionist view, the attention is on the way in which elements interact with one another, and by interacting with one another generate, as a result, new, sometimes new identifiable dispositions of elements. So in the first case, position comes before interaction. In the second case, interaction comes before positions. All this can be seen as a premise to the concept of relative structural invariance, which also Laurie was referring to. Essentially, I mean, the principle is simply that in a complex organized network, there are certain elements which are relatively invariant with respect to other elements of the same network. This principle has a very important not only empirical, but also theoretical implications. And of course, as I was already referring to, Herbert Simon, in his well-known paper on architectural complexity, 1962, considers an application, or in a way an analog of relative structural invariance by speaking about intermediate stable forms and considering intermediate stable forms as a dominant feature of non-physical or complex networks. He makes explicit reference to biology, and I would make reference also to socioeconomic networks. Well, an important implication of relative structural invariance, which goes back to Gunnar Myrdal, it's a statement he made already long ago in the 1930s, is that in a system in which you have different elements moving at different relative speeds with respect to one another, what is emerging is the problem of order of motions. So certain elements can, to a certain extent, cannot even move before other elements have also moved. Then I basically propose, and this is what comes out of my own original research framework. I think that production networks, on which there has been a long research tradition stemming at the very least from the Nobel Prize economist Vassily Leontiev on complex production networks. And but in the field of complex production networks, I think it is very important to formulate production interdependencies by putting emphasis on the relative invariances. Different elements of the production system don't move normally together. There are certain elements which can move because of structural conditioning more quickly than others, and vice versa. Of course, all this in relative invariance of certain elements of a production network relative to other elements generates what we may call a hierarchy of motions. Gunnar Myrdal used the concept of order of motion, which entails the idea of a hierarchy of motion for different production activities. Just think of the different components of a supply chain, of which we hear much talk nowadays. But more generally, I think that this set of concepts, this, I would call it an organized set of concepts, can provide useful conceptual tools for the analysis of organized complexity, not only in the case of production arrangements, but in many other social fields as well. One application, one implementation of relative structural invariance is that if we look at a complex organized network, we may discover different distribution of invariances across different elements of the network. And of course, if we compare organized networks, social organized networks, having different distribution of invariances across its different elements, what comes out is the likelihood of different pattern of responsiveness to dynamic impulses. So perhaps even different degrees of resilience vis-a-vis certain impulses or shocks. Now there is an important, I'm approaching the conclusion of this set of reflections. Now, there is a point on which I would like to call your attention, and which I think is quite interesting, quite important at least, namely that given a certain organized network, we can offer alternative structural specification, namely alternative representation of organized complexity. And alternative representation of organized complexity, may I also recall the mentioning of multi-layer networks, which was done by the previous speaker, may entail different patterns of responsiveness again to dynamic impulses. All this, I think, would invite us to reflect on the distinction which was initially outlined, I think, by the mathematician Lotfi Zadeh, between possibility versus probability. Possibility entails essentially understanding of boundaries within which certain events can take place. Probability, we know what it means, is the likelihood of certain events to take place or not. I remember in one of his papers, Lotfi Zadeh makes the interesting example of a car which can only fit 5 people. So possibility tells us that that car can only fit 5 people. Probability is a different concept. It will tell us whether it is more or less likely that there will be up to 5 people in that car. Why the distinction between possibility versus probability is interesting from this particular perspective? Well, because understanding of relative structural invariances, understanding of the distribution of relative structural invariances in a particular system or across different different complex networks may allow us to identify which specific ranges of opportunities, namely which specific dynamic trajectories are feasible in a particular production network, without necessarily, almost never actually, without telling us which specific trajectory will actually be followed. That's why the distinction between possibility versus probability is central. On the other hand, this distinction provides, I think, a combined role for theory on the one hand and for contingency on the other hand. Theory becomes a fundamental, conceptual apparatus which would, if correctly applied, allow us to understand which constraints, opportunities, and even affordances are inherent to each particular structural specification of a complex organized network. But that would not be enough to understand which specific dynamic trajectories will be followed. For this, we need an appropriate understanding of contingency. Contingency is essential because basically, unless we deal with contingency, we are unable to explain why social actors take particular actions and why structures follow specific trajectories. Well, this is what I wanted to say. Thanks.
Thank you, Professor Cazzieri, and sorry again for the error before. I don't know, Aura, can we go if there are some questions now, and then we move to the next? I think we have to move to by the time we move, I already, so let me thanks. I still have a lot of questions about synchronization, timescale, synthetic data, and entropy, but I will keep it for the end.
Yeah, for the discussion.
And now for me, it's before giving the floor to Aura, which will host and co-chair the next section. For me, it's a very big honor and a pleasure to welcome Professor Sir Alan Wilson from the Alan Turing Institute of London, UK. It's a pleasure to hear him talking about new application of entropy maximizing model. I will never try to make a short version of a contribution to Sir Wilson to the field, because otherwise it will take all the afternoon. I don't know if Aura, you would like to introduce our next honor speaker. Thank you very much.
Okay, so I just say in a simple way that Professor Sir Alan Wilson is for us the father of entropy. I think this sentence just explains what do we feel when we see him, and all his work, because starting from entropy, then he went on complexity. And then I would like to leave the floor to him and thank him a lot for his participation, his cooperation. And really, I look forward also to continue the cooperation with him and also with his great mind. So Alan, the floor is to you.
Okay, thank you very much, Aura, and thank you and your colleagues for that kind introduction. It terrifies me sometimes when I think about how I first got involved with the entropy concept, because the paper which introduced it into urban modeling was actually published in 1967, which is now over 50 years ago. And what I want to do today, in part, is to reflect on that, and that's what I was doing in the book. And I want to do something unusual, I think, relative to the other contributions today, and certainly relative to Mike and Peter, my colleagues who will follow me, because there are a number of people here today for whom the notion of entropy will be totally familiar, but not in urban modeling. Whereas what I thought I would do is actually introduce you to the basics of the concept using a very simple model, and then go on to say something about research priorities, and particularly in a way continuing the discussion on organized complexity, which we've just been having. So let me share my screen. Let me see if I can find, get this onto full screen. Yeah. Okay, so let me kick off. I mean, I'm going to talk about what I call an iconic urban model. It's one that I like to talk about when I'm introducing entropy in urban modeling to particular audiences. And some of you, as I say here today, will not be familiar with these applications. And I'm going to talk about a retail system, because we all understand retail systems and how we choose to shop. And so that's the model that I will use. You've already heard from introductions about Warren Weaver talking about systems of disorganized complexity and organized complexity. And the spatial interaction model that I'm going to talk about only works for systems of disorganized complexity. And then I'll move to how it can be a component of models of organized complexity. So let me show you the model as an example. And to fix ideas, think of retail in London. And on the screen now is a map of London. The yellow blobs are retail centres by their size. So the largest one is the West End of London around Oxford Street. And there's something like 200 retail centres in London. And if you can just about see them, the pale blue dots are the centroids of wards in London, of which there are about 600. And so what a spatial interaction model is going to do is to model the flow of expenditure from each of those 600 residential centres to potentially any of the 200 retail centres, or of course in that matrix that I've just defined, there'll be a very large number of zeros or very small numbers. And again, if you're not familiar with urban models, and my colleagues, I hope, will forgive me for starting in a very elementary way, but just so that you can actually see how some of the mathematics works if you're not familiar with it. Let me show you how I would build up the notation. So you could actually pick two zones, let's say Hampstead, Central London. You could have a flow, which I'm going to call the flows S, from Hampstead to Central London. That becomes a bind, so we actually introduce numbers. So if Hampstead is zone 23 and Central London is zone 1, we have a flow from zone 23 to zone 1. And then, of course, we generalize that and we talk about the flow from zone I to zone J. So in the example that I'm using to illustrate this, I can be from 1 up to 600, which are the residential zones, and J can be 1 up to 200, which are the retail centres. So that we have an interaction, a spatial interaction table, which would have 120,000 entries. And so you can imagine an origin destination table, origins I 1 up to 200, destinations J, 1 up to 600 for the I, 1 up to 200 for the J. And what we do with entropy maximizing models is to find the most probable value of the elements of that matrix. And we look at, and again, you'll be very familiar with this is a microcanonical ensemble in physics terms, which are the bottom rows. You know, what are the possible microstates? Find the microstates that are consistent with various constraints, and then that will give a prediction of the flows. So the formal notation then is I've defined the flows from a zone I to a zone J, Sij, a travel cost or some measure of impedance, which I've called Cij. We're doing retail, so I'm going to take EI as the average expenditure from population of I, PI being the population, and I'm going to take WJ as the attractiveness of the retail centre in J. So we're going to model, using entropy maximizing principles, the flow of expenditure from a residential zone to a retail centre. And the beauty of that is if you go through the entropy maximizing calculations, you actually produce that formula. If you maximize an entropy function subject to constraints, I'm not going to go through the detail of this, you get, for my 120,000 possible elements, Sij, you get that formula. So in effect, you're saying the flow from I to J is proportional to the expenditure in I, the attractiveness of J raised to a power, and it's inversely proportional to some declining function of impedance, travel cost, distance, whatever measure you are using. That's why in olden days, pre-entropy maximizing, a version of that would be called a gravity model, because EI and PI looks like one mass, WJ looks like another mass. And then if we were being Newtonian, we'd divide by Cij squared. But what the entropy maximizing method does is to give you a much more general method, a statistical averaging method for estimating those flows in a way that works very well. And we can interpret all the terms. The AI term is a measure of competition. So the flow from residences to one particular retail centre will be determined by the competition of other retail centres, and the AI handles that. And in particular with this model, and it's part of the utility of the model, we can actually sum over the flows into a retail centre J from all the residential areas I and calculate the revenue, the total cash flow into a retail centre. So this is all very aggregate stuff. To do it in reality, you have to disaggregate it. But again, I hope that will give you an idea of developing a model which is quite widely applicable. So what I then want to do is to just flick through half a dozen slides. So I'm saying I've got the 120,000 flows captured in one equation, just repeated through all the i's and j's. And then when you're actually trying to run one of these things, you have to disaggregate it. You have to set the EIP term and do all the research on expenditure for different kinds of people. You have to take the attractiveness term and work out how to get a good measure of attractiveness. That gets you into quite complicated formulae. So if you disaggregate, this is from a real case, and you're trying to get a measure of attractiveness in J for different kinds of people, different kinds of shopping, different kinds of retail, you have that kind of formula. So the simple model becomes quite complicated when you make it realistic, but the principle is the same. So disaggregate from that WJ to the alpha to a WJ with superscripts representing much more detail, and then you can make it work. You can calculate the revenue with summing over the flows. It always looks incredibly simple. So if you actually substitute for Sij and for AI, you see that we're actually doing something quite complicated to reproduce the revenue in a particular retail center. In a minute, when I want to move on to organized complexity, I want to be able to say if I'm a developer of retail centers, or this could be particular stores, but let's say a retail center for the sake of argument, I want to make an estimate of the cost of running a retail center. And so if I take WJ, again, to illustrate as a measure of size, I take KJ, that big KJ, as a unit cost. That gives me a rough estimate of the cost of running a retail center. So if I take then the revenue minus cost, that's the DJ minus KJ, WJ, it tells you whether it's profitable or not. And out of this spatial interaction model, if you use that measure of profitability, we can actually build a dynamic model which gets us into organized complexity. I'll come on to that in a second. CIJ, I introduced the notion of a generalized cost. You can combine money costs, travel time, different kinds of travel time to get a good sensible estimate of this. So again, another element of the model which looks simple, but to represent reality can become it can represent quite complex factors of the way we all behave. And so what you're then doing is combining all these. There are two key parameters in this. So WJ to the alpha parameter says how important is attractiveness in determining these flows. If alpha is greater than 1, you have scale economies. And so that's important to discover empirically. And beta determines, in effect, the average length of the trip in these kind of spatial interaction models. High beta means short trips, low beta means longer trips. You have, when you're trying to run these kind of models, the really interesting thing that came to me very early on, because it's totally obvious, when you do the entropy maximizing process, the impedance function is a negative exponential function, and that's the one that I've been using on this slide, the e to the minus beta Cij at the top there. The old gravity model would have had Cij to the minus beta. And the really interesting thing is if you replace Cij by log Cij, then of course that transforms from the negative exponential function into a negative power function. And the beauty of that is you can then actually when you actually calibrate these models, you can actually investigate which of these functions fits best. And then you can actually interpret them. And of course, what it means is that if the power function fits best, a logarithmic measure of impedance is better than a linear measure of impedance. And so what you will find is that the negative exponential function works better for systems where the trips are shorter, or if you're doing something like long distance airline trips, then the odds are, because we perceive the impedance logarithmically or more like logarithmically, a power function will fit better. So all sorts of interesting things you can do with the model in different circumstances. I've talked a bit about competition, and you can obviously put all that together. And then I threw one other slide into this, which is just to say, in the early-ish days, not very early actually, we're talking late 80s, early 1990s, working with a colleague, Martin Clark, in Leeds, we actually set up a university spin-out company called GMAP that applied this model in all sorts of real-world contexts. And what this slide shows are the large companies. This is retail in a very broad sense. It can be it can be shopping, it can be banks, it can be car sales, and so on. And I throw this slide in just to show that one of the things that's particularly interesting about this this model is it's not simply a theoretical concept. These companies paid GMAP and the university large sums of money to optimize their retail networks. The biggest client of GMAP was the Ford Motor Company, where we were doing their strategic planning for 13 European countries. And so again, I'm trying to give you a simple model that introduces the background of entropy maximizing and the use of entropy in urban modeling. But this slide, just to show that it's highly applicable, and indeed still is. And of course, what's been interesting over the decades that followed is that while, in fact, GMAP still exists, while there are companies that still do this kind of work, the big companies, like the big supermarket companies, have simply internalized this sort of analysis, and they run these models in their own analysis teams within their companies. So that's what I want to say by way of introduction to the model. And then I want to connect it to some of the things that have already been said about systems of organized complexity. But start with two things. The main point of the retail model has been, as I've described, to optimize networks in the sector. But obviously, it's a component within a broader urban model. But the beauty of this system is that it can be applied in any system which involves spatial interaction, can be represented by weak interactions between individuals, and therefore it's a system of disorganized complexity. And that means it could be applied to schools, colleges, universities, general practices, hospitals, prisons, and it has been quite widely applied. But it's actually been more applied in retail. I say this with a bit of a smile, because it's been very clear to the users who actually improve their profitability by using the model, you know, what their main indicator is, which is actually improving their profits. It's very much more difficult to get those kinds of measures in the public sector. It's not impossible, but it's been more difficult to actually introduce these kind of models in health, for example, although we've done a certain amount of that. Anyway, the final thing that I want to say is to then connect this and the way this model can be used to move on to systems of organized complexity. And I'm going to stick to the same illustration for these purposes and ask a different kind of question. In modeling spatial interaction so far, I've assumed that the retail structure, which is effectively all the WJs, the attractiveness of sizes of different retail centers, are given, the given variables for running the spatial interaction model. But we can ask the question, how do those systems themselves evolve over time? And I'm going to use that profitability measure to turn it into a dynamic model. And in fact, what you then find is you have a model of that represents phase changes, and I'll give you other examples of what you can in principle do with it. And again, to illustrate this, I can state the idea in terms of a very simple kind of equation. So remember, DJ is the revenue attracted into a retail center, and KWJ is the cost of running it. And what you have there is a differential equation on the rate of change of WJ over time. And that is simply saying that if a retail center is profitable at a particular location, it will grow, or conversely, it will decline if that is negative. And just to indicate the scale of the challenge that we now have as analysts, is if I go back to my London example, there are 200 retail centers. So there are 200 differential equations, and the DJs in particular involve all 200 variables for any one of those 200 equations. So you have 200 simultaneous differential equations in 200 variables. And it's in that set of equations that you have to start looking for phase changes and interest in dynamics. And we can do that. So it does give us ways of exploring future scenarios, particularly now in terms of the increasing recognition of the sustainability agenda. It's also been interesting in terms of the pandemic, another big current issue of how to integrate this kind of spatial interaction model with epidemiological models. And again, some really good work's been done in that kind of territory. So that's what I want to do, Aura, by way of introduction, to give you an idea of what the model looks like, to say it can take us into a wider range of applications beyond retail. It can become a submodel because you still have to have the spatial interaction components within a dynamic model. And the dynamic model gets us into much more complicated territory in terms of the modeling challenge, particularly in terms of phase changes. And again, I should probably end just by giving you one very simple example of that to show how it works in practice. None of you will be old enough to remember the late 1950s or the early 1960s, but food retailing used to be in what we would call corner shops, small shops. And in a very small space of time, supermarkets took over. And that was an example of a phase change in these kinds of, that can be represented in these kinds of dynamic models. And so looking for those kinds of phase changes. And we've more recently used it, for example, looking to predict areas that are about to be gentrified in cities. And again, when it happens, it tends to happen very quickly. And you can look for the phase changes in dynamic models that would enable us to anticipate that. Anyway, I'll stop there, Aaron. I hope that's left plenty of time for any questions that or comments that colleagues want to make. So back to you, Ara.
Thank you a lot, Professor Sir Alan Wilson, for your contribution. I'm sure, I don't know if there are questions from the audience. If there are anyone remotely from Zoom who would like to ask a question or make a comment, you just open your microphone or raise your hand. Otherwise, I see a question. Please, would you mind? Guest, in the microphone, or you can turn on the red light.
This is Kieran Donahue, and I think I raised my hand, but I don't know if it's been recognized. Thank you very much for that excellent presentation, Sir Alan. I'd like to ask a question about some material in your slides that you didn't get to discuss, and that is the interdependence, more on the theme of interdependence of different types of activities. And in 1985, in an article that you published in Environment and Planning A with Bennett and Haining, you talked about how you could take these spatial interaction models through a hierarchy of steps that Zeeman prescribed in the advance of a science. And in that progression, there were both fast and slow variables that were changing, and the slow changes were the parameters and the fast were the variables. And it seems to me that that type of modeling would be very useful in modeling rebuilding the built environment, insofar as we know that infrastructure is long-lived and lumpy and leads to path dependence in a lot of other areas. And it seems to me that the systems that you have elaborated here and elaborated with your co-authors in that paper back in 1985 would be very useful in getting to grips with some of these challenges at a time when much of the built environment is in the United States falling around our ears and has reached the end of its service life, and points to the need to think about how to reconfigure not only particular communities and cities, but also mega regions and systems of cities. So I'll stop there and see if you have any comments on that.
Yes, I think that's a very important observation, and I'm interested that you refer to that 1985 paper, because I think that's a long time ago. But I think, as you imply, these kind of questions are still very much live, and it's probably more important even today that we can actually tackle them. I mean, in terms of the illustration that I've been using today, the SIJ variables and the spatial interaction model represent fast changes because they're actually equilibrium models. And there's an implicit assumption that if there is a change, for instance, in the impedance factor or in the attractiveness of a particular retail center, the response in terms of where people shop, the spatial interaction change is very rapid. What is much slower, and it's an example of the slow change that you refer to, are the changes in the WJs, which in effect are the changes in the built environment. And so modeling that or attempting to model that is more difficult, and you rightly say it's extremely important. In terms of modifying scenarios to meet sustainability challenges, for example, it could be very, very important to actually look to what would have to be changed exogenously to bring about phase changes that would take us towards more desirable futures. And I think there's there's a huge amount of work to be done there. One of the things that we haven't talked about is with these dynamic models, you talk about path dependence, which is extremely important. And a way of looking at path dependence is to see it as a series of initial conditions. If you think of running the dynamic models through discrete periods, you go from one period to another period, and then you have a new set of initial conditions to carry on. And path dependence will really show through that. And phase changes will intervene from time to time. So basically, I'm just saying, yes, what you're describing, I think, is one of the most important contemporary research problems for using these kinds of models. It's the kind of thing that I know Mike Batty, for instance, has done a lot of work on recently, and he might comment on it later, although I think his main topic is a slightly different one. But you're absolutely right.
Thank you. Thank you for the question and the answer and the discussion. There are two more questions from the audience here, and then the third question from online. And I take the responsibility that we go through them, because I think that this part of answering questions is the most interesting part, one of the most interesting part, because it means that the talk has been stimulated a lot of consideration and questions. So I would like to have our guest, Professor Peter Nijkamp, and I apologize for the pronunciation, to ask his question. Please.
Thank you. Thank you very much, Mr. Chairman. And thank you, Alan. I'm very happy to be here this afternoon with participants from the far Western hemisphere of our world, like Kieran Donaghy and Laurie Schintler, but also colleagues from the more Eastern-oriented hemisphere of this world, like Otto Hudak and others. So I'm very pleased to be here. Thank you, Alan, for your exposition. I happened to be a lucky person because I was just trying to calculate when we met for the first time. My calculation, my memory, this was in 1970 at the European Regional Science meeting at LSE in London.
Yeah, I think that's right, Peter, yeah.
So ever since, I did not forget you. It was nice to see your retrospective, but also your prospective view on where it all started and where we are going. The question I have for you, Alan, is the following. I think I would not have any critical comment on your perspective on the complexity phenomenon of modern cities. You gave the illustration of the retail sector, but of course there will be many other sectors like public services and what have you. But the question I have is in particular on another part of the modern cities, or two parts perhaps. On the one hand, the citizens, and in a modern city, of course, there are economic dynamisms involved, but a significant part of what makes a city is made by the citizen. I just refer to an old book maybe of the well-known German philosopher, but also urban scientist Max Weber, with his famous book, The City, not a city, The City. And the city, in his view, is a human construct. It's not only economics, it's on what people are doing and the way they structure their activity. I think nowadays we try to model some of these things also through SNA, social network analysis, and a few other quantitative elements like agent-based models and so on. But how far can we integrate that type of new, more quantitative sociological thinking on cities into the more economic and economic geography oriented perspective you have offered? That's my first question. The second one, there is another category of actors in the city. And that's not only business or services or the citizen, that's maybe even not governments, but governance. We are very happy to have with us this afternoon one of the former mayors of the city of Bologna, one of these beautiful cities. And it's nice to have her with us because the question on how in a democratic or even in a non-democratic society urban futures are shaped is an important one. And if we are not in China, but in other parts of the world, then we know that there is a strong degree nowadays of citizen participation and citizen engagement. And we know that no city will ever evolve in a proper way if citizen participation is not guaranteed. And increasingly also in political science, we see nowadays models, statistical analysis of how to shape citizen participation so as to combine the interests of both the economic sector and the social and community sector. And I was wondering how that type of new perspective could be incorporated in your thinking. So these were my questions, Alan.
Yeah, thank you, Peter. They're excellent questions, and I will try to give you responses, but in each case, they would need to be much more fully elaborated than we have time for. I think on social behavior as distinct from economic behavior, I think even with the example that I've used, it's not difficult in principle to transform what I was calling impedance, combine it with what I call the attractiveness function, and to represent the model in terms of a utility function. Now, I know the utility function in its normal sense is an economic concept, but it's also possible to interpret it in these kind of models in a social concept and to represent social behavior. So I entirely agree with you about the importance, if I can put it in a slightly different way, of not assuming, as it were, economic determinism, but add in social determinism. Sorry, determinism is the wrong word. Probabilities, actually, because everything we're talking about with these kind of models is about probabilities. So very, very brief response to say, I think we can extend the models to incorporate more sociology. Let me put it that way. And I'm not sure the sociologists have really helped us very much, actually, to get beyond, the dominance of economics in terms of the paradigm that we work with. And I'm all in favor of, more interdisciplinary routes for the models that we work with. The second question, the governance question, I think is a very interesting one. And I'll respond to that again in anecdotal terms. A relatively small number of years ago, I chaired a British government study, which was a foresight study on the future of cities. And we paid great attention, actually, to engaging with the wider public. And I think the way that this can be done with the kind of models that we all work with, and it connects to actually what Roberto was saying about possibilities relative to probabilities. Since there are so many uncertainties in trying to forecast with these kind of models, what we can do is explore a great variety of future scenarios. If we explore future scenarios and then raise questions about what do we do now to progress towards better ones rather than worse ones, let's say in terms of sustainability, or indeed in terms of a wider set of social objectives, then that can be done, and that can be used as the basis for public engagement. And we did this very successfully in terms of that particular study by having mini foresight exercises. And in the UK, for example, in Newcastle and in Milton Keynes, Milton Keynes actually set up a Milton Keynes and MK 2050 commission to explore these kind of future scenarios. So I think there are possibilities of doing this. I think the real problem is then that while from time to time, and I'm sure we've all done this in different ways, we've attempted to do this, it is extremely difficult to sustain it. And I'm not sure there are many examples of what I think I would like to see of cities having their own futures lab with an analytics-based exploration, systematic exploration of different possible future scenarios that will then enable much more and better informed debate about possible futures and how we move towards good ones and avoid bad ones. So I hope that makes sense, Peter, but a couple of really good questions and some general responses on what can be done in each case.
Thank you again for the question, the answer. I mean, this is a topic that probably will deserve 1 week of consideration on how to embed social or citizen behavior into our model. For some politician, it will be just a viscosity term, but probably we should do better than that. And thank you very much for this exchange. I think we should move on with the question. Probably the final discussion and the coffee break, it will be a little bit shorter. I take responsibility for that, but it is very important that we touch this problem. So I don't know now Professor Reggiani has a question, and then we have the last questions from Denise from online. But first of all, Professor Reggiani, please.
Okay, so I would like to thank Alan for the inspiring presentation. Also with Alan, we met in Turin the first time, and then during my PhD in Amsterdam, I went to meet him in Leeds. So really, Alan, thank you also for inspiring all my work, my PhD work, and also nowadays, I would like to say. And we met also other times in London and so on. And my question is related to an old challenge, because your fundamental book, Entropy in Urban Regional Modeling, really inspired a lot of persons, not only myself. And I think that the great discovery of your book, of your mind, is just the fact that by maximizing entropy, you derive a spatial interaction model. Okay, so this for me is really something of exceptional, just showing on the one side a sort of interpretation of entropy as a sort of utility function, aggregate level, and then we go back also to the question of Peter, and why, you know, at the micro level, the individual, more or less, I was thinking just on those years and also nowadays, can follow the axiom of independence of irrelevant alternatives. Why? Because it has been demonstrated that a spatial interaction model also is equivalent to a logic model. So then I'm asking to you, after several years, do you think then that by maximizing an entropy model, you assume that the world and the citizen are following the IAA axiom? So that's more or less is constrained. And then since also by means of McFadden, we had just the nested logic model is overcoming this axiom, can entropy also embed this hierarchical model, this nested logic model, and just overcome this micro interaction of citizen in a logic way? So that's my old question, old challenge.
Well, it's an interesting question, clearly, Aura. I must admit, I tend not to think in IIA terms. So I'm probably not the best person to respond to that. I mean, I convert that in my mind to assumptions about weak interactions. And the reason why entropy models work is, for instance, if you're modeling something like the journey to work, we don't all consult each other about where we travel to work in the morning. You know, we function independently, but within a complex environment, which is in effect what we're modeling. I mean, what I find, and it's a sort of indirect way of responding to your question, and one of the things I've always been interested in, when there are alternative modeling approaches to what is essentially the same problem, you know, in this case, modeling spatial interaction, entropy maximizing logic models, netted logic models, or whatever, I'm always interested and have spent time trying to find out what the underlying commonalities are between the methods. And I think in terms of the logic models, it's actually relatively easy to reconcile them by looking at the assumptions that have been made about the distribution the statistical distributions that underpin the logic models. And you don't have to go very far down that line before you find you're reproducing entropy models. So I think those kind of connections can be made. I mean, what appeals to me about the entropy maximizing method still now, relative to the other methods, is it's well defined and powerful and has nothing mysterious about it. Whereas sometimes with other approaches, you're still making assumptions which have, if I can put it this way, an element of mystery. In fact, I've just been rereading, and I recommend to anybody who wants to have a think about the basics of entropy, Schrödinger's classic book, not on quantum mechanics, but there's a very short book by Schrödinger called Statistical Thermodynamics, and he gives a beautiful introduction to entropy maximizing, which is effectively, what I took on in my early days. And what he says in his opening chapter is, which is very similar to what I had in my slides. If you can do this and you can understand this, you can actually do the whole of physics. And it's a huge claim, of course, but coming from Schrödinger, it was a very interesting one. But to answer your question more directly, Aura, I think all these approaches can be reconciled with a bit of hard work.
Okay, thank you.
Thank you again. I will. Sorry, yeah, to Denise. I move to Denise. Please, you can open your microphone and camera if you want. Please, it's your time. Thank you.
Yeah, thank you very, very much. I don't want to be long because the day is short, but I'm delighted to meet you again, Alan. And my question was, as a previous one, oriented towards the time in the question of urban dynamics. And you did a marvelous work with this maximization of entropy model for try to analyze and predict spatial interactions inside the cities, and the operational models is really a great success. About its dynamization, I wonder if there is perhaps, as we make differences between the scale of one city and the scale of a system of cities, isn't a problem of temporal scales in the evolution of cities, the one being this kind of rather short-term reaction between supply and demand, for instance, for which the model you develop fits perfectly, and models of urban future which may imply other dimensions that are constraining the time of evolution, and that would be perhaps not only come from the inside of the city, its actual configuration, but from what is happening elsewhere in the other cities and in the world. Don't you think that there are qualitative differences in those both temporalities that are interfering in the development of cities?
Yeah, I'm sure that's right, Denise. In fact, I still I do think, and I'm very aware of all your work and that of your colleagues on these kinds of dynamic analyses. And I was saying in relation to Ara's question, in terms of spatial interaction, where there are different approaches, it is possible to draw them together. I think the same will be true of dynamical analysis, actually. And, I'm conscious that the work I've done in this field, which are basically using those differential equations, and instead of Boltzmann, I'm using Lotka-Volterra mathematics. But you're absolutely right that there's a wider range of factors that need to be taken into account. And I think we're only at the beginning of that process. And given the challenges of sustainability, pandemics, security, then I think all I can say at this stage, and we're running out of time, it's the beginnings of potentially a long research agenda. I'll just make one final comment, if I may, Chair, and so this is slightly different to your question, but one of the things that I raised was then a few times was security, and the notion of spatial interaction as threat. Gets you into a totally different area of modeling, which we've done some work in. And I think by introducing a much wider range of factors and differences between different cities, will involve richer models, Denise. I'm sure that is true. And I think we have a long way to go to do that.
Yeah, thank you.
Thank you, Denise. First of all, I invite you to thanks again, Professor Sir Alan Wilson, for his talk and also for the question and answering section, which I found very, very interesting. We will come back to this to the end. And if you allow me, I suggest that we move on to the section 2. About discussion on complexity. I would like to invite Professor Roberto Scazzieri and also Professor Federico Palmonari, both from the Bologna University, will join me and help me to guide this section. And while they take seat, I would like to spend 2 words about the next speaker. I'm very, very honored to have Professor Michael Batty from the University College London. I'm not trying again to list all his affiliation, which they can be overcome only by the list of awards that Professor Batty had in his career. And it's me an honor. I just want to mention, especially for the young student or everyone going to the field of urban dynamics, urban evolution, of understanding such complex system, even from different areas. I really would like to mention 2 books. One is Fractal City by Professor Batty, few years ago, but at least for me, very enjoyable to read and very influential. And first of all, and finally, I would like to mention a new book, a more recent book called The New Science of Cities, which I had the pleasure to read from the beginning to the end, and not only contains a wonderful review and background of the developing of model in the realm of urban complexity, but it really gives, at least in my opinion, a very interesting and stimulating perspective for the future of this kind of studies and research. So I don't know if my guest want to say something about my co-chair.
Thank you so much. You have given all presentation needed. My name is Federico Palmonari. I am a fellow of the class of physical science of the Academy of Science, and on behalf of the Academy, I am very happy to introduce also Professor Batty to this prestigious audience. And I am only to say that also in complex system, the material composing the complex system obey physical law. So in a sense, physics is present also in complex systems.
Well, simply, I think we should give the word perhaps to Professor Michael Batty, who is giving his talk on explaining order in urban density and city size distributions. I believe that Professor Michael Batty, the floor is yours.
Thank you. Okay, so, well, Chairman and audience, I've changed the title slightly from complexity to scaling. In fact, if we look at the book, Entropy, Complexity and Dynamics, to some extent, the concept of scaling sort of runs through many of the chapters in this sense. But I thought I would pull out this context of scaling. Originally, I thought I would talk a bit about how entropy and scaling were related in a sense, but it's a big topic that, and in some sense, I've sort of veered towards a safer topic and to tell you a little bit about what's going on in scaling. Now, many of these ideas are in fact have been developed over many years. For example, many of the equations we use, the relationships we use, are in fact scaling. We've only recently begun to think about what that means. Let me also say that if you want a copy of this particular PowerPoint as a PDF, then you can actually go to one of these links. The best one, if you can take a photograph of the screen if you want to, but the tiny URL at the bottom is Y6MWZ75R. I'm sure you can't remember that basically, but I'll state it again at the end. So if you'd like to have a look at the PowerPoint at your leisure, or the PDF, I should say, then please do from that link. So let me begin with a simple visual summary of my talk on different types of scaling in urban systems. I'm going to develop ideas about 4 different types. There may be many more than 4 types of scaling to some extent, and we can discuss this, of course, in the questions. So I wanted to, as I said, to present a paper on scaling and entropy, but I wasn't able to develop the links, although I will say something a little bit about entropy, because to some extent, the parameters of scaling equations that scale, and there are many of them. We've seen a number this afternoon already. Alan's basic equations, where he talked about the negative exponential and the inverse power functions, are effectively scaling equations in that sense. These are really signatures to some extent scaling of complex systems, just as entropy is also another statistic. And I think it was either Aura or Laurie basically said that maybe entropy has the seeds within it to become a much more unifying concept in terms of complexity dynamics and entropy itself in that way. And so in some sense, this is the essence of what I'll be talking about here. I should also apologize to Denise, who Ara sent the paper that I originally was going to do to Denise. So Denise, I think, was mandated to raise a question at the end of this talk. And of course, she's read the wrong paper, basically. But I think that Denise has done a lot of work on scaling herself, in a sense, and we'll be able to certainly, embrace in some sense what I'm saying here. Okay, so these statistics, entropy, scaling parameters, are signatures really of complexity in that sense. And what I'm going to be talking about are urban systems that in 2 dimensions that can be seen in terms of landscapes, if you like, which are full of, which are based on single centers, poles and spikes, and also polycentric centers. And in some sense, the scaling parameters and the entropy systems relate to systems of this kind. So I'm going to actually begin with a simple example, basically, which in fact is shown here. Let me tell you what this is. On the immediate left, these are models or idealizations from Frank Lloyd Wright. On the immediate left is the Mile High Tower, the Illinois, which Frank Lloyd Wright speculated would be a tower which could contain an entire amount of population in a city. And this was a speculation back in 1957. 20 odd years, 25 years before that, he'd also talked about Broadacre City. So the second picture on the top is Broadacre City, which is essentially a uniform one-dimensional city, a city of bungalows, if you like. So this is the extreme. If we measure the entropy of the Mile High Tower, basically, and there's nothing else in the infinite plane in that sense, can compare it to the to Broadacre City in this sense, then this difference, if you like, represents the space of possibilities for all cities. So if we're interested in compact cities, then we're more towards the Mile High Tower. The Broadacre City, in fact, is the city sprawl, basically. It's the one-dimensional city. It's like Phoenix and many of the southwestern US cities in that sense. And then the next pictures along is Le Corbusier, who talked about the city of tomorrow, and this was in 1924. And you can actually see that the city of tomorrow on the immediate left is basically a city which is somewhere in between, if you like, the Mile High Tower and the Broadacre city in that sense. If we try and abstract in that sense, we can think of the Mile High Tower if this is the one-dimensional version in some sense, and you can think of all the activity being packed into that particular bar in that sense. If we think of Broadacre City, we can think of it as this in a sense, and this particular picture I've just shown is the city of tomorrow, Corbusier, and of course cities that we've been talking about, which to some extent are based in this notion of the impact of distance, really, related to where the action is in the center, etc., are shown by the very typical die-away function, decay function, basically, of distance or travel time or whatever it is, that is really central to what Alan was talking about, and indeed some of our previous speakers as well in that sense. So to some extent, we can measure these are all scaling, and we'll see in a moment how to do this, but at the same time, we can also measure the entropy of these things. I've actually put down loosely what I think the entropy is. The entropy is essentially zero. If you measure entropy using Shannon's formula, where we have n events, so we divide our city into n locations, and only one of them is full of development in that sense, then the entropy is zero. It's a highly ordered system. A highly disordered system is where we have the no constraints, really. Everywhere is the same, basically. So entropy in that context equals, I should say, entropy equals log n, basically, I should say, rather than n in the sense. And then in between, we have these entropies. Now, of course, we can also fit scaling parameters. We can fit scaling equations to these things. And the scaling parameter, if we think of the inverse power function for the Mile High City, the scaling parameter is equal to infinity in that sense. For the suburban sprawl, basically, the scaling parameter is equal to 0. Somewhere in between, we have 0.5, and then the inverse power law, which is the classic example on the left, on the immediate right, I should say, has a scaling parameter of about 2. So let me tell you how we can go about these and think about them. This, to some extent, is what we're doing. We're fitting, really, a relationship of this kind, and this is really the simplest way to a one-dimensional ordering of development in this sense. And you can see the possibilities with respect to the inverse power shown from these pictures here. I should say that to have in mind the notion that y equals k with x to the minus alpha, where alpha is the scaling parameter, is essentially the so-called inverse power function. And a lot of these scaling relationships really relate to that. Okay, now I'm going to organize the rest of the talk dealing with 4 types of scaling, and I've called these 4 types after the key individuals who are first associated with their development. And these are often referred to as laws in a rather casual sense. The 4 individuals who I've named these after are no longer with us, although it might be argued that these types that I'm going to talk about are better ascribed to others who are still with us in this sense. And the 4 laws are all based on variants of the power law, and they are Zipf's law, which relates to the rank size rule, Clark's law, which relates to the negative exponential, Tobler's law, which is a generalization to some extent of Clark's, and Marshall's law, which in fact really relates to questions of size and agglomeration, and to some extent the development of scaling in complexity theory, certainly based on the work coming out of Santa Fe, which has come out of Santa Fe over the last 10 or 15 years, is really a rather different kind of scaling from the first 3 in this particular context. But we'll see as we go along what this actually means. Okay, so I'm going to go through these fairly quickly. Zipf's law, or the rank size rule, is the most generic. It relates to the regularity in a cumulative frequency of events that follow a power law when we rank their sizes from big to small. And in its pure form, this law suggests that the size varies inversely with the rank. So if PR is the rank of the population, in that sense, there's a constant proportionality. And then if we divide that constant by the rank, basically in that sense, then we have Zipf's law, which in fact he formulated in the 1930s. Basically, it's contained in his book, Human Behavior and the Principle of Least Effort. And indeed, although he applied it to cities, he applied it perhaps more extensively to word frequencies. And indeed, still in the literature, and there are many, many papers written on Zipf's law since then basically city size distributions and word frequency distributions are still, to some extent, the main things. Of course, to some extent, Zipf's law is really a law that relates to competition between events, basically, in that sense, in the notion that if we think of it in terms of cities, then we're talking about a small number of big cities and a very large number of little cities in that sense. And of course, to be a big city, you have to be a little city first. And therefore, if you think about some sort of casual kind of determinism where small cities are trying to become big, basically, they can't all become big because of limited resources, then there's a lot of models, stochastic models. Simon, for example, developed a model of that sort, a lot of models of that sort, which explain the rank size rule in this way. But it's the most nihilistic to some extent of all our scaling laws, because to some extent, it's really sort of not explaining city size with respect to some sort of independent variable. Okay, we can easily demonstrate that this law is scaling in the sense that if we scale or multiply the size, which in this case is the rank, by some constant, lambda, for example, then the equation scales proportionately. You can see that from the simple derivation there. And a more generic law following Zipf, of course, assumed that the scaling parameter alpha was equal to 1, a unity in that sense. But a more generic law is given by the equation at the bottom of the screen there, which where we have alpha raised to a variable power. There are some limits on what these values should be in some sense, and in terms of fitting them, there's been quite a lot of activity over the years in thinking about these limits. Okay, so let's have a quick look at what this means in terms of rank size. The picture on the top left-hand side is employment density in London with respect to rank going out to about 50 kilometers. What we did to get this is to actually take the rings, basically, the annuluses. We used the original Clarke formulation to count up the number of annuluses, and we actually then looked at the numbers of the density in each one of these annulus and plotted it. And of course, if we go from the first annulus to the number 50, that's 50 kilometers out, basically, then it's a kind of a rank. As well as a distance, it's also a rank. And you can see that the rank size rule fits rather well. When we take logs of it in terms of the X and Y axes, employment density and the rank, basically, we can see the bottom picture is quite a good fit, basically. And at the other extreme, on the right-hand side of the screen, then we've taken the top 14,000 cities from the Global Human Settlements Database, or Global Human Settlements Data Layer, in a sense produced by the JRC, and also I think Season in Columbia are involved in that project. But there are, according to the GHSL database, about 14,000 cities, greater than about 50,000. And you can see we've plotted those going out to the rank of about 14,000 in a sense, and you can see that we've got that at different points in time. And even if you go back to Zipf and his work in his 1949 book, basically, then he has a picture of the relative stability of this rank size rule for US cities from 1801, from 1790, I think, to about 1930. And this is, in fact, more evidence, if you like, of the stability of this rank size. Towards the end of the talk, I'll come back and say a little bit about what happens at the heavy tail and what happens at the long tail, because these are very important features in terms of scaling. Okay, this is the NordPil database. It's a UN database, basically, of 750 or so cities from 1950 to 1925. And you can see the impact of the long tail in this particular database. There's a lot of issues concerned with where we cut these things off and the relationships that you actually get as you begin to manipulate the data in this way. Okay, so that's Zipf's law. Now, Clarke's law, we've already seen this afternoon. It's based on the observation from his 1951 paper. And I should say that Clarke is by no means the first person to do this. I think, as Peter Nijkamp said, Max Weber probably talked about it, or one of the Webers talked about it back at the turn of the last century. But anyway, it's the observation that population density declines inversely as a function of distance from some central point. And of course, Clarke originally postulated the law not in terms of a power law, but as a negative exponential. And that really connects it directly to spatial interaction. I'll come on to that in a moment. He said in his paper, the falling off of density follows a simple mathematical equation of exponential decline. And you can see immediately that we could translate that by assuming, for example, that the distance was a logarithm in that sense, as Alan showed earlier. Then this turns it very easily into a power law. And it has the same form, to some extent, it's scaling in the sense that we demonstrated with Zip. Some examples of this, this is London out to 50 kilometers, and then London out to 200 kilometers. London out to, if we look at the right-hand side of this rather than the left-hand side, that's the inner part, the inner part of London. But London out to 200 kilometers takes us almost as far as Manchester. And when we actually produce the rings of the 1 kilometer rings as we move out, then this smooths it quite dramatically. Were we to actually take the actual densities of employment densities of the basic census units, the MSAs and so on, then it would be much more sort of scattered in that sense. But we can smooth it in that sense. Clarke, in fact, and several people in the middle of the last century talking about these things actually used the idea of smoothing the data, in the sense that it became less popular as our computers and mathematical instruments got a little bit better, basically, but it's still an interesting way of thinking about the impact of density. It smooths it in some sense, giving you a better picture of the inverse decay. And let me say that also one of the things that's interesting, and I don't really exploit this in this talk particularly, but we can actually look at the idea that distance away from a particular point is also a kind of a rank. If we think of the distances as being ranks, basically, in that sense, then we can actually, in that sense, assume that the rank size rule is almost the same as the traditional Zipf law, where rank is not thought about as distance in that sense. Anyway, there's an interesting implication in that sense that nobody really has worked as far as I can gather on thinking about the Clarke model as being a kind of a rank size rule in that sense. Okay, now my third example of scaling is Tobler's law. Now, of course, to some extent, Tobler's law is similar to Clarke's law, but it's defined by Tobler. It's widely referred to in this way in geospatial analysis, in GIS and so on. Everything is related to everything else, but near things are more related than distance things. And that, of course, to some extent, takes us directly to spatial interaction, which we could say is Newton's law, basically. Newton's second law, but also in present company, without sparing his blushes, this is also Wilson's law. But I'm only naming my laws after the dearly departed, right? Not the nearly departed, which we all are basically in a sense. But anyway, this is just a sort of an addendum. Okay, there's our gravity model equation, basically, with one scaling parameter, And we'll see a little bit later that we can put more scaling parameters onto it, and that takes us through to Marshall. Now, I think that Alan also responded to Kieran, who asked a question, and Alan then, I missed it a little bit, but basically, of course, we have a large model of the UK that we can generalize, and you can see here the patterns of spatial interaction, the patterns of scaling in a sense. And this is a very good example of scaling in that sense, that we take the Northwest, the little kind of inset basically, and blow it up. We can see these patterns really at all scales, basically, in a sense. These are the vector, these are the average flows, taking the flows between all origins and destinations. There's about 71 million of them, potential flows in this particular model, because it covers the whole of the UK. But if we look in that particular context, then we can see that we get scaling in that way. Now, I'm not going to take that any further, but of course, once we begin to map these ideas, then this is the sort of thing we get. And that takes us into the world of fractals and things of that sort, really, in that sense. Okay, last but not least, and in some respect, this is what many people in complexity theory mean by scaling. There's Marshall's law. Now, this is the law of size, in which an object or event gets more than proportionately bigger or smaller when it changes its size, in that sense. This law lies at the core of allometry, which pertains to changing shape as an object grows, and the best examples being ourselves, and I'll show you a picture of that in a moment. There's Alfred Marshall, who was the great English economist from the late 19th century. He didn't quite articulate this law of size, in a sense, in this particular point, but he made the point, which was translated by a succession of economists after him into the idea of scaling and agglomeration. We could call it West's law after Jeff West, but Jeff is still alive, so we won't call it West law yet. But there are lots of people whose laws whose names we could use for this, who've talked about it. Okay, there's a quote there from Marshall. That's as far as I've found. And the law can be stated as follows. It's very different from the inverse power laws. The law can be stated as, and this is, I'd better give some substance to these variables. Y is income, if you like, and P is population. So the law is stated that Y is proportional to population raised to a power, in a sense, and it's that power which is referred to as the allometric coefficient or the scaling constant. It can either be less than 1 or greater than 1. If it's greater than 1, that means that income goes up more than proportionately with population size. And this is very much the favored development of scaling in urban science, really, in city science and our world. Developed by Louis Betancourt and Jeff West, basically, in a paper in PNAS back in 2007. They resurrected, really, this idea in that sense. And there's a good deal of controversy about it, in a sense. One of the other features, of course, is that it's probably better to look at that scaling law in terms of the equation below it, basically, where we've normalized it for population itself. Okay, so here are some pictures of the Betancourt-West relationships, in a sense. You can see the idea of change. The idea on the immediate top left is the classic allometric equation that as people get bigger, they're all normalized to the same height, basically, in this picture, but as they get bigger, they change in shape. And to some extent, when we apply this to cities, this is what we're looking for. It's quite difficult to actually find examples of this in the literature. That in our fractals work way back, we never really looked at how fractals scaled. I know that Laurie showed a picture from our stuff of London, basically, where you could see the sort of scaling if you sort of aggregated in your own mind at different levels. But there's not that many good examples of what Betancourt and West are really saying in terms of the changing shape as cities get bigger, in that sense. Okay, the two graphs there are wages versus population and wages divided by population, the two equations, basically, the two graphs for 1969, I think, and about 2008, basically. So you can see the growth. And you can see that the the scaling relationships, and the key thing is to look at the scaling coefficients, basically the coefficients in the equations, which in the graphs in the middle there, and also the graphs on the right-hand side, which are the same but normalized differently, then you can see that the allometric coefficient is well greater than 0. It's 0.1 basically in that sense. That probably means that if the population goes up, by X amount, then the whole lot goes up by 1.1 by 110%. Basically, population goes up by 10% or by 100%, then the income goes up by 110%, something like that anyway. Okay, now I don't have any good examples, as I said, about real city shapes. What I'd like to see out there is similar to what Darcy Wentworth Thompson did, where he showed these pictures of fishes, how they're distorted in some sense in that way, which is the classic allometric demonstration. But when we look at data from the UK, this is the relationship we get in that scaling relationship in Marshall's law. In terms of wages and the log of population, there really isn't much that tells us that wages go up proportionately for most of the British cities. In fact, London is a massive outlier in that sense, much richer than everywhere else, but everywhere else is more or less the same. You know, if you're in Manchester, which is a big city, then you're not likely to earn much more than, you know, small city sort of Sunderland or something like that. Okay, on the right-hand side, we've got business services, which do show positive allometry, and quite strong positive allometry in this particular context, but more of a scatter in that sense as well. Okay, so this really is the work that's come out of scaling from the Santa Fe group, and there's a lot of it basically at the moment. Okay, so a couple of things. There is quite a lot of controversy about superlinearity or positive allometry, positive, in a sense, economies of scale. Because the implication is that if you want to get wealthy, you go to a big city. It doesn't take account of anything to do with what goes on inside the city. So the city may be getting richer, but the number of poor might actually be increasing quite dramatically within it, in the sense that the riches and their gains might be outweighing the poor in that sense. So there's not been that much work done on that. And also in Britain, it seems like the relationship is linear between wages and city size, and many people, such as Henry Overman and so on, they argue that maybe London is too big, or maybe the rest of our cities are too small when we compare them to other parts of the world in that sense. So there's quite a lot of substantive stuff that really flows out of that. Okay, now I'm just very quickly going to say that a couple of things. Zipf's law is pretty nihilistic in some sense. But a couple of things that are important in Zipf's law, in terms of the heavy tail, the bigger cities basically, then often you can see situations where you have what Didier Sornet calls dragon kings. This is where the biggest cities are not big enough. And then in terms of the long tail, basically, in that sense, then this to some extent has to be probably dealt with in some way, because the long tail in these city size distributions does give us an indication that perhaps we're not talking about power laws at all. Perhaps we're talking about log normal distributions. Okay, that's another debate. Clarke's law, basically the issue about Clarke's law is the reason why he chose the negative exponential was that the inverse power law, as the distance goes to 0, basically then the value becomes infinite in that sense, and therefore Clarke suggested a negative exponential. So indeed did people like John Tanner, basically, who was a traffic engineer years ago, back in the days when 1959, 1960 that Alan referred to. Tobler's law, that incorporates really Clarke and Marshall, basically. It's both allometric and inverse in that sense, which to some extent is what the spatial interaction models are in that sense. Marshall's law is problematic because of this question of how do we normalize it when we're looking at these relationships. They look very good, very high correlations, in a sense, but once we normalize them, then they're not so good in that sense. Okay, thanks for listening. I could say a lot more about this, and there's a lot of links towards entropy that I'm working on a bit, and so maybe some questions will come up. Denise may have one, and at that point I'll hand back to our host and stop sharing. Okay.
Okay, thank you very much.
Okay.
Okay, I think we are short of time, but let me just say that in terms of your references to Marshall's law, I think there are at least two important precursors of Marshall's law in economic theory. One is what we may call Smith's law, with his well-known direct relationship between division of labor and the extent of the market, and an even more direct precursor in economic theory is by a relatively little known Neapolitan economist writing in 1613, Antonio Serra, who explicitly addressed the issue of Venice as a city, saying that there was clearly a direct relationship between the size of the city, the number of artificers working in the city, and the level of productivity in that city. So basically, a rather direct precursor of Marshall's law. Okay. Now, I think that, of course, we are a bit short of time, but the floor is open to questions. Okay, please. Yes, I think it would be useful.
Thanks, Professor Batti. Nice to meet you again. We meet more than 10 years ago, but I don't want to. I am Armando Bazzani.
Oh, Armando, yeah, I remember very much. Yeah.
So my question is, in some sense, very general. As a physicist, I can justify using a maximal entropy principle, the exponential law, because it's the Boltzmann law when we have a preservation of energy and just we take the maximal, the measure which maximizes the Gibbs entropy or information entropy. It is more difficult for me to justify a power law from a maximal entropy principle. So my question is, what is your idea in order to make the maximal entropy principle consistent with the scaling law that we observe in the city or in the mobility and so on?
Well, I mean, I think this is a question that goes back to Alan to some extent, that that he made the point, Alan Wilson made the point that to some extent when we fit the relationship, and if we find that the power law is a better fit in certain circumstances than the negative exponential, then we look at what's being fitted, and the implication being that the power law is more likely to fit a system where distance is treated logarithmically, or travel time, or whatever the measure of spatial impedance is. So that really says nothing particularly, I think, about the Boltzmann hypothesis in any particular context. So in some senses, it's the pragmatism of estimating these things versus the theoretical origins in some sense. And I'm not aware, although maybe in physics this is the case, I'm not aware of any grand theory that enables us to develop scaling in the sense that I talked about. To some extent, the four examples or the four perspectives, if you like, are sort of somewhat ad hoc. They're somewhat empirically reasoned in that particular context. Do you want to, Armando, do you want to say a little bit more about that and try and give me a hint of what you're getting at, really, in that sense?
In some sense, the idea that I have is that you can justify this kind of power law when you have, for example, a structure of I talk about transport system, when you have different layer transport system and you have more than exponential law that lives together, and then you will get a convolution effect, and you can see the rise of a power law. So in some sense, it means that your systems has no scale because it has many scale inside the microscopic dynamics. This is my impression. And this is what I see also a bit on the data for mobility, for example.
Interesting.
Yeah, so in other words, different layers, if you like, of mobility, different layers, if you like, and these must relate to some extent to our perceptions of distance and impedance in that sense.
In some sense, the logarithmic that you insert in order to pass from an exponential law to a power law is inside the dynamics in which you have a logarithmic scales in the microscopic dynamics. This is an idea that I think could justify the rise of power law in say complex system like cities. So
very interesting. Okay.
Okay, thank you very much.
Interesting. I think we have a question from remote.
Denise, why don't you go first? I've also been asked by Aura to ask a question, but I think you have prepared remarks that pertain directly
thank
to
you.
what
I waited for the permission. Thank you, Mike, for reinserting the question of scale in the classical geographical knowledge and existing models, which help to think about it. I also agree that besides the Zip, Clarke, and Tobler, it's very interesting to consider Marshall's law, which may have been preceded. There are also insights from sociology. I'm thinking of Tard, for instance. And perhaps I wonder if for putting the basis of such a theory of scaling, we could specify a little more regarding cities about attempts at theorizing, which would not be made only of mathematical models, but of integrate more proposals about social behavior and the way the spatial configurations evolve. And for instance, I'm thinking of Christaller, because in Christaller's model, who are adapted to a given stage of urbanization, but there is a consideration of relationship, proximities, and not only size of cities. So the location is integrated in this model. And I'm thinking as well as to Hegerstrand's model of innovation, spatial diffusion of innovation, because it is also based on the way change is occurring in geographical space, starting with a micro observation of the behavior of individuals, and getting until the spatial configurations that are produced by such type of spatial interactions. So I also like very much, because someone said about Antonio Serra, before that there is Giovanni Botero, who wrote in 15,035 or something like that, about grandezza e bellezza delle cose, della grandezza e bellezza delle città, which indeed put the basis of the complexity, meaning multi-dimensional competition occurring between cities either among Italian cities of the Renaissance or even in the new colonies in Brazil. And it is the same type of interest that have to be taken into consideration for people being in charge of the development, resilience of such the governance of the city of the time. So I think, what he says could apply to the way cities are still competing today. So my question is about what, of course, there is a universal skeleton of theories of complex systems, but we need, don't you think we need to specify more completely what is peculiar to cities and systems of cities to develop the application of those ideas about complexity and even entropy?
Yeah, I mean, one of the things in this talk that I was very conscious of, that what I didn't want to do was to try and propose a theory of scaling that related to cities. I didn't want to do that because I think it's very ambitious and it needs a lot more thinking by a lot more people. But I'm well aware, as you know, Denise, that all of this stuff goes back to Christaller and, you know, back into the 19th century and so on. And there are lots and lots of different links in the edifice of knowledge that's been created in terms of spatial systems, human geography, and so on. In fact, if I could just say that when we did our book Fractal Cities that was mentioned, we got into fractals, Paul Longley and me, largely me in that particular instance, we got into it because of computer graphics, right? And it was only when we began to look at what work had been done spatially in terms of cities, and we began to look back, that we discovered there were all sorts of people writing about fractals way back. Long before Mandelbrot, basically, a lot of work in map generalization, in geography, and so on. And so the notions that I can entirely empathize with the idea that we need a much more integrated view about how we put these ideas together, basically, in that sense. And these bits that I've shown are really the obvious bits, basically, that we can all agree about. The equations scale in a certain way and so on. But the wider edifice is very important. One of the reasons why I didn't want to, I wasn't able really to do very much about entropy and scaling in that sense, is that a lot of the scaling work reduces the urban system to one dimension, basically, in a sense. The entropy work, to some extent, reduces it to one dimension. But of course, cities are two-dimensional, or three-dimensional, or n-dimensional in terms of interactions. So, in other words, there's a whole set of ideas to be developed where we're talking about a much richer notion of interaction. And that's really where a lot of these ideas from Hagerstrand and Christaller and so on come in, really, in that sense. I don't think it would be too difficult to, and there are people who've done bits and pieces on this, basically. It wouldn't be too difficult to tie some of these things together. In fact, I think to some extent, people like Peter Haggart, basically, in his two books, Networks in Geography and Locational Analysis in Human Geography, back, you know, in the late 1960s, basically, simply by putting those reviews together, he was beginning to make those linkages, and lots of people have done that. You've done that, and so on, in a way. So I entirely empathize with this notion of thinking about a much grander edifice, if you like, of how we put these ideas together. That also relates to Armando's comment too, to some extent. If we had that, then we may be able to make some more specific progress about relating, you know, power laws to negative exponentials and so on.
Thank you.
Do we have other questions?
I've been asked by Aura to to ask our speaker a very provocative question.
Go on. Ara doesn't want to ask it then.
Well, I would like to. I have read both papers that were pre-circulated closely, but I'd like to ask a question that I think pulls together some threads from our morning's discussion. And I would preface it by first saying, John Friedman's definition of planning is the management of change in territorially organized systems. And so if we look at the comments that have been provided here in terms of trying to steer a morphology in a particular direction, say a more sustainable one, and one of your opening observations was that scaling statistics are signatures of complexity that apply to systems of variegated morphologies. We also have the observation that's been made by Roberto Scazieri and Roberto Pacciuelli on the distinction between possibility and probability. And Peter's comments earlier about the social aspects that underlie these spatial forms. I wonder if you could speculate on integrating some of the material that you introduced in your book, The New Science of Cities, on using the mathematical sociologist James Coleman's model of collective decision-making to talk about how we could use that model to discern what's possible, what is reachable in terms of getting to a different morphology based on what the social dynamics have to tell us and what the scaling models have to tell us about the range of possible urban morphologies.
Okay, a lot of questions there, Kieran. But let me try and deal with the question about the mathematics of the James Coleman mathematics of collective action. I mean, for those who don't know, in my book, The New Science of Cities, in part 3, I deal not with models really of urban systems in the sense we've been talking about them particularly here, but I actually deal with ways of changing urban systems by looking at how networks of things that influence them can actually be used to actually produce new designs of various sorts. And one way of thinking about that is to identify the factors that influence the design of a city, a future city, with the stakeholders who have an interest in that design, and therefore we can think of them as social networks in some sense. I should say that part 3 is the bit of the book that nobody ever reads, basically, that if you actually sort of ask a geospatial scientist or something about that particular book, they won't know what you're talking about when you get to part 3, basically, because they've never been trained in architecture and planning and all these other things. Nevertheless, it does raise a very interesting question, and it's back to, I think, maybe it was your question or Ara's question to Alan about how we introduce sociology to some extent, or the social dimension into these models in that sense. And I think there is some hope that we might be able to think about, dealing with small groups or even large groups for that matter more systematically. I mean, network science is a very good illustration of this. I mean, for many, many years in sociology, people dealt with networks, but it really wasn't until A, computers got big enough, and B, lots of physicists began to discover this world that we got real sort of progress in thinking about very large networks, in network science, basically, with people like Duncan Watts and Laszlo Barabasi and so on, working on all this stuff. And in some senses, I think there's quite a lot of very interesting work in behavioral networking and behavioral science and so on, which is potentially could begin to enrich many of the models that we've had in that sense. I wouldn't go any further than that, but I think there are some real possibilities I wouldn't go any further than that because I don't know quite how one would do it, but I think there's some real possibilities of making progress along those lines with respect to enriching our models in that sense. How it relates to scaling, I don't know. I mean, that's a bridge too far to some extent in terms of thinking about making proposals for how it might relate to what I talked about in the scaling stuff. But there are relationships. Obviously, as soon as one talks about formal structures, I should say that one of the reasons why, I sort of said this a moment ago too, one of the reasons why it's very hard to think about some of the things I talked about as being the best signatures of complexity is because complexity to some extent depends on interactions, basically. And in most of what I talked about, there was very little on interactions. Okay, Tobler's law says a bit about interactions, but and to some extent, but it's a sort of hands-off. Scaling is often a hands-off view of interactions in that sense. So that's an issue. It's back to this notion about what's related to what, in a sense.
Okay. If there are no other questions, are there questions?
No, I don't see anything online.
Yeah, nothing. Okay.
No.
So I think we should probably have a short break.
Yeah, now I need to be the bad guy because I want to be coherent with the usual Italian punctuality. We are going to have a just 9-minute restroom break, probably without coffee because we will have coffee later. So we convene again here at 5:25 because I don't take time to the third discussion on spatial dynamics, and then I will invite Professor Silvia Giannini and Professor Roberto Patuelli to join me. So we are going to have a very short rest break and blame me for everything. Thank you very much. No coffee. Okay. After this long break, we are going to move to the third section. It's about spatial dynamics. Very happy to have here Professor Silvia Giannini and Professor Roberto Patuelli, both from the University of Bologna. I leave them the role to introducing the next speaker. We are very honored to have Professor Nicampo here in Bologna. Please, colleagues,
Yes.
go ahead.
Okay. Well, so I'm super happy to introduce Peter. As you may have guessed, Peter was my supervisor, was our supervisor. So we have a long history, and I'm all with gratitude for Peter. Peter Nijkamp was a professor at the Vrije Universiteit Amsterdam for many years. He has also in his career, and in particular during my PhD, has been the head of the Dutch Research Council. So he also had let's say a high-level administrative, let's say leadership position in the Netherlands in terms of scientific research. He received many prizes in his career. I think the Spinoza Prize in 1996 was maybe one or the most important, is the highest scientific honor in the Netherlands. Professor Nijkamp also received several honorary doctorates from universities across the world that would be difficult to list. And of course, he's well known as an extremely prolific researcher, most in particular spanning with his research let's say, across many different realms, from regional science to, of course, urban and spatial economics, to environmental economics, to many different fields, moving also beyond what is the normal span of a specialist, in this case, moving beyond economics, which is where he's coming from originally. What else I wanted to say? Let me check. Okay. No, two more things. One thing I wanted to underline of Peter, which is something for which I always admire him, is his ability to work with many different authors of different age and level of expertise and level of, let's say, seniority. So, of course, he works with other prestigious scholars, but also with many young scholars. Peter is very generous in his way of lending a hand to young researchers and helping them building their career. Of course, I benefited greatly from this, and Aura is the same type of attitude toward young scholars. And so I think this is something that characterizes Peter, and that I always liked, and that I always highlighted when describing him. That he is very also generous in working with not only with others, say celebrities in science, but also with many young scholars and helping them. So I think this is, in my view, one of the best ways to introduce Peter as in terms of his behavior and attitude toward young people. So Peter, I think the floor is yours. We are very eager to hear what you're going to talk about, and you can go ahead. The title, I don't have the title, but
yeah, the title is The Blessing in Disguised Hypothesis on Natural Disaster and Threats, Resilience Benefit from Shocks. Thank you very much.
Thank you. Thank you so much. If you don't mind, I will stand up, because I've always told my students a teacher has to stand. So I will stand. Let me begin by saying how much I appreciate to be here in the sacred halls of the Accademia delle Scienze in Bologna, a fantastic building where the frescoes reflect also parts of our ancient history from on the interface, the interaction between Greece and Italy. Before I start to be more serious, let me tell you a small anecdote, and then I will be more serious. I'm myself a fellow of the Royal Netherlands Academy of Arts and Science, and we have a golden rule in our academy. And President Scacchieri, where is he? Okay, but it doesn't matter. He will certainly like it. Also, Aura will like this. If the president of the academy asks someone something to do, you can never say no to the president. So if he asks you something to do, and if you don't like it, you say, yes, President. It means I don't like it, but you do it, right? But if you like it, then you would not say, yes, President. Then you would say, it's a great honor, President, right? Okay, so the same here. When at some stage I got a letter to be here with you today, through Aura and Riccardo Scacchieri and some others, but on behalf of the president of the academy, I was invited, and of course I answered with excessively great pleasure. I did not say yes, but excessively great pleasure. So for me, it's a great honor and a great pleasure to be here, and I hope we'll have in the next half hour or so, or 1 hour, depending on the time, a nice discussion. One of the advantages of being in an academy setting is, of course, at the end, we do research, but we also critically reflect on research. And the thing which brings us today together, in fact, has been this great book, which has been edited by Aura and several others also here around, Roberto, Laurie Schintler, and Danny Czamanski, and of course with many co-authors, etc. Nice joint community work, and it brings together a whole range of different reflections and models on science. I was asked to talk in this second part of the afternoon, in particular on spatial dynamics. What I've done, I will talk later on in a few minutes, in particular on something which is close to my heart, which I nowadays call the blessing in disguise theory in spatial dynamics. But before doing so, just a few more general remarks. You see, in the beginning, there was geography and there was regional science, but it was rather, let's say, non-quantitative. Gradually, after the 50s, the 60s, last century, we got into what was called the quantitative revolution in geography, in spatial planning, in regional science, etc. But the quantitative revolution has different stages. It is not just one revolution, it has different stages. It started first with a deep analysis of statistical data. We were collecting data, a deep analysis of statistical data. And then later on in the end of the 60s, 70s, we got more the modeling aspects, etc., trying to replicate complex realities by using mathematical models. Later on, we realized that life was not always very linear, so we had to deal with non-linearities. And of course, that was replicated in spatial interaction models. We have seen the contributions by Alan Wilson and by Michael Betti, but also our Reggiani has played a major role in developing concepts like chaos models, synergetics models, later on complexity models, and a whole range of models which in fact try to replicate or to deal with nonlinear complexities and so on. And of course, at the end of the day, and that is more the beginning of this century, we realized that even when we have this whole range of different models, we are not yet able to fully understand. And then, of course, the claim came up, we need more data. And of course, then we got the big data movement. And that, of course, has been flooding our disciplines and has led to an enormous breakthrough also in our analytical efforts, how to replicate the complexity, the spatial complexity, but also the social complexity, economic complexity of our world. And but gradually have now also realized, even when we have tons and containers full of data, do we get a better understanding of our world? Do we now understand our world better than 20 years ago? Can we make better predictions? That remains to be seen. And that means that nowadays we also say, well, we need more complicated methods for handling the complexity of our spatial and economic and social realities and urban and regional realities, i.e. artificial intelligence, machine learning techniques, etc. And that prompts all kinds of scientific debates on, can we understand our world without solid theory? And that's an ongoing discussion in many disciplines, including in geography, planning, economics, sociology, and of course in physics and medical science, etc. What is the role of theory when we have a data-rich environment? And I think this is one of the fundamental questions. Now, one of the things I am very much interested in recent years is the issue, not that much of complexity in itself. I mean, that's the building blocks where we start from. But the main question is, if there has been let me put it in a neutral way, a non-linear evolution of certain phenomena. It could be a shock. It could be the Arab Spring. It could be a pandemic. It could be an earthquake in Turkey. It could be anything. If there is a non-linear shock, how can we handle this? And what is the mechanism so as to understand? In the past decades, there has been a rich movement, especially in resilience theory and vulnerability theory and fragility theory, etc., so as to get to a better understanding of the equilibrating forces after a perturbation in a normally smoothly developing nonlinear system. But the question then is, what are the long-run impacts of such shocks? Are we going back to an equilibrium? Yeah, that's a simple question. But what kind of equilibrium? We have not that much of, let's say, hope that we will always get back to the same equilibrium. And if we want to get back to the same equilibrium, that might need enormous transaction cost. I give you one example. I will not destroy the furniture here, But here, I should put it up on the table, but doesn't matter. Here's a chair. The chair is now in a stable position. At some stage, we can put the chair like this, and beyond a certain tipping point, the chair suddenly falls out. To get the chair again up is an enormous transaction. It's much easier for a chair to fall down than for a chair to get up again. So beyond the tipping point, the forces you have to put in place in order to get back to the same equilibrium is enormous. And now the question is, what does that mean if we then study social systems, economic systems, cities, urban areas, regions, countries, etc. And that brings me then, in fact, to, so after this long introduction, that brings me then to the aim of my presentation this afternoon. The follow-up of spatial dynamics in the form of recovery potential and the forces needed and what are the long-run implications of a system brought out of equilibrium, but with some effort being put back into equilibrium. So I have asked our friend to get the slide. The Yep. So we get the slide in. Oh, it's not from here. No, I thought it would be held. Yeah. Okay. No problem. There we go. No. Right, and then. Okay, there we are. Okay, sorry for the interruption. I was some misunderstood with distance control. Let me, so here is the title of the presentation, The Blessing in Disguise Hypothesis. And I, in particular, apply this to natural disasters and threats. And I look into the resilience benefits of shocks. And the title already suggests a daring idea, i.e., shocks can be very good for you. Disasters can be very good for you. I know this is a daring hypothesis, and I can tell you I've given this speech a few days after the earthquake in Turkey, and I was heavily criticized because of my positive view on a disaster. And I had to defend myself and to indicate what I meant with a blessing in disguise hypothesis. But it's, as we know in science, is not only on a belief. Science at the end of the day is on theory and facts and verification of facts through theoretical models. So that's the only test question we need to apply also here. I will begin with a very simple example, which in fact comes from the origin of this university in Bologna. Some of you, and certainly our friends from Bologna, may have seen the Archi Gymnasio, right? Which was one of the foundations of this university many centuries ago, with beautiful frescoes, etc. But of course, in the course of time, somewhat dilapidated, and it was partly destroyed in the war. And you would say, how terrible, an ancient building partly destroyed. But nowadays, and we have seen it this morning with a group of colleagues from the university, when you go there nowadays, it has been completely restored. The frescoes have been repainted, and it looks much nicer than ever before. So thanks to the bombardment, it has led to an enhancement of the quality of cultural and historical heritage. So we can be very pleased, at least from that perspective. So the question we have now is, can we apply this simple idea, which I just take from a coincidental example in Bologna, can we apply this simple idea of a blessing in disguise? Can we apply this also to a broader context? And yes, I argue it can be applied to a broader context, but it needs to be proven, of course, otherwise we can't believe it. So there we go. in the framework of the famous book, which we have just, we are celebrating today. Here I start with another type of example. Italy is supposed to be a Catholic country. I guess all Italians will know what is happening on the 18th or 19th of November every year. That's the day named after Saint Elizabeth. Okay, so that's a holy day. In the year 1421, so almost more than 600 years ago, a major flood and a major huge storm hit the coast of all the countries around the North Sea. And a significant part of the country of the Netherlands, it means lowlands, was completely wiped out. Thousands of people killed, the whole western part completely flooded. One of the major cities, Dordrecht, completely flooded, and a total disaster. In less than 100 years later, Dordrecht was the political and commercial center by then of the Netherlands. Later on, it got hit by the Spanish War, but in any case, by then it became the flourishing center. Apparently, the flood, the Elizabeth flood, named after Saint Elizabeth, was very good for Dordrecht. Of course, you would argue, but there is human suffering. Yes, of course. That's terrible. We should not forget it. But from a long-term perspective, now it comes from a long-term perspective, not a temporary suffering, that's always terrible. Long-term perspective, it did very good to the city. It became a flourishing trade city, international, etc. So, this is an example, one of the examples, and I can tell you about many things on the blessing in disguise hypothesis. At the end, it was very good for the city. That whole theory and that framing has recently been published just a few weeks ago in Socioeconomic Planning Sciences, which is a rather long article where we have been working together with my co-authors Alex Banica and also Krima Kurtit and some others from the University of Iași in Romania on a testing of the blessing in disguise hypothesis applied to natural disasters. And of course, to do so, you need lots of data to test, of course, what is happening. Let's start a little bit with some more elementary ideas, and then later on we get to the theory and the statistics and the modeling side. So the question is here, disasters as opportunities. Are they windows of opportunity? And here you see pictures of cities and areas destroyed by floods, by earthquakes, and so on. And the same applies, of course, to wars. In passing, one of the things in which we are involved nowadays is indeed the reconstruction of cities in Ukraine after the Russian war, the war with Russia. And there, of course, the question is almost the same. And it's a very serious question. And we have been visiting Ukraine also recently a couple of times. If a city is destroyed, partly destroyed, completely destroyed, like Mariupol, etc., the first thing people want is to have a house, which is quite natural. You want to have a house. But if you build the same house, you make the same failures in your planning concept and in your strategic view on the city, you rebuild the problems from the past. So can we help these people, the planning authorities in different cities, to quickly rebuild things while knowing that you cannot rebuild exactly the same house because you need to have better insulation and you need all the other modern things, etc. That's a major challenge. So what you want to do is go back to the first situation, destruction. Then you want to go back, but in fact you want to, that's also what is nowadays called building back better. You want to build back, but it ought to be better, otherwise you replicate the mistakes from the past. So you want to have a higher equilibrium. In fact, that's what an economist would argue. So that brings us into a concept. Yes, all of you are familiar with this, on resilience concept. On the left-hand side, you can see, in this case, we mentioned there's a conflict, but it can be any disaster, an earthquake, a flood, a war, it doesn't matter. Things go down because investment in infrastructure is destroyed, gradually get a filtering down effect up to the level where you reach more or less a lower point, so it's a U-shaped curve, and then gradually it's a task of good government to rebuild, but to rebuild better, right? So you have to go up. And if you are a little bit of an optimist, you will see that the right-hand side of the U-shaped curve, which requires a lot of interest and attention and effort, that's why I showed the example of the chair, you have to do more, but in the long run, you can have a recovery trajectory. And if you are really smart, really have smart governance, you hope and you realize that at the end of the day, things will even be better, not after 1 year, but maybe after 20 years, etc. So that's the point. So, and in fact, that brought us, also inspired by previous works of our Reggiani on resilience, we call this prosilience. Re means you go back to where you are, there's re, right? But pro means you go forward. You do not only want to go back to where you are, you want to improve. So that's why we have introduced here the principle of prosilience as a guiding tool for planning of urban areas which have been destroyed. And in some publications, we have tried to also empirically demonstrate this by means of data and modeling, what prosilience could mean and how it could be measured. Just quickly then on, because this is rather familiar from if we have natural disasters and there's a resilience or a prosilience question, of course, we may go back to some of the older works on resilience. Now, we have with us our Reggiani, who is an expert, and I have to tell you that even though there is quite some work on resilience by Martin and what have you, Aura has already 20 years ago published one of the first articles in our field on resilience, and can certainly be seen as one of the leading persons in this field of spatial dynamics. But the question is, of course, always, should we replicate the declining curve and do exactly the same where we came from, or do we have to do different things? And so that has to do with the opportunity space which we have in our field, geography, regional science, planning, social systems, and complex systems, and so on. And of course, that brings us into the blessing in disguise hypothesis. Now, a few simple things. We know that if there is a forest fire, in the short run, it's not good for the forest, but in the longer run, it creates more ecological stability in the forest. And if that is a metaphor which we can use can apply to human societies, why would it not apply in the longer run to human society? It's almost the same thing. So together with another colleague of us, Borsekova from Slovakia, we also have been working on the long-run benefits of urban disaster as a conceptualization. And later on, we have tried to work that out also with different colleagues. I was in particular inspired by this whole idea of this daring concept of blessing in disguise by an article which was published a few years back in a journal of regional science on the effects of bombing of German cities by the Allied forces. And it's an interesting article, and it talks about, it's a sort of experimental
approach, German cities were heavily bombed during the war. Leipzig was almost destroyed, but also Frankfurt, and so enormous disaster. If you compare the cities which were bombed compared to the cities which were not bombed, and then if you look 50 or 60 or 70, the question is then, which city is doing better? And it turned out that most of the German cities bombed during the war are performing better than those which were not bombed. So some sort of a natural, almost natural experiment. And of course, you can explain this, because if you bomb a city, and if you decide not to rebuild the city in exactly the same form, but you create a new city with bigger streets, etc., and then of course look into Frankfurt and look into Düsseldorf and whatever, that is true. So after the war, after beginning the 60s, the 70s, they had better accessibility. They could perform economically much better than all the old cities which had narrow streets. They could not expand, etc. They were limited in their economic activity space. But the bombed cities could build a new city, which was more geared toward efficiency goals in the post-war society. That was a very interesting article. I can tell you, and there's just a local anecdote, but it's a story or so. The city of Rotterdam. I don't know whether some of you have been in the city of Rotterdam. The city of Rotterdam was bombed, whole inner city bombed in the beginning of the war. Completely wiped out. It had the same architectural history as Amsterdam. If nowadays you go in Amsterdam, you walk around in a historical monument. Rotterdam is just modern skyscraper city. It was completely wiped out. After the war, the people of Rotterdam said, we do not want to be remembered anymore of all the people killed, etc., and all suffering. We want to build a new city. And they did. Rotterdam, if you're on the city center, I don't like it, by the way, but doesn't matter. But it's a modern, architecturally designed city. It has become also the center of modern architecture nowadays. So thousands of people all over the world are visiting the city for a very experimental architecture, very daring architecture. Whether you like it or not is not so important, but it is a very spectacular type of architecture. And Rotterdam, of course, performed very well after the war. It became the biggest, or almost one of the biggest ports in the world after Singapore, etc. It had completely rebuilt its port function, and it did many, nothing remembered of the past, only looking forward. And so it has had an impact, a very positive impact on the economic growth of the city. So having mentioned now a couple of examples, there are many, many more, of course. Let's then go back to where we are. The first question we have to look into, apart from the modeling side, is what is better? That seems a naive question, but if things are destroyed and if after 50 years we look back, are things better? But what is better? And the scientist has to measure things, whether they are better or not. And of course, normally a traditional scientist or economist would say, well, we look into average income or economic growth or so. But nowadays, that is not anymore the best way to look into city evolution. So what we have tried to do here is to use, in fact, the Human Development Index, which is a, let's say, a rather well-accepted index also developed by United Nations and also supported in the SDG, the Sustainable Development Goals movement, etc. And that has a range of different indicators, not only economic, but as you can see here, also health indicators, knowledge indicators, education, culture. So, but everything is measurable. So what you want to do is essentially measure the HDI index and then see how it develops, if possible, over the next number of years from the beginning up to the end, and then see whether it
leads to a better performance. So we are not only talking about economic welfare, we're also talking about the well-being index, because the HDI is essentially a well-being index. So that once you have this, of course, you have to look into the question then whether there is a resilience or a prosilience dividend. Is it good to be effective or not to be effective? And of course, that has led to enormous debates, and not only in Europe, but also in the United States. And some of you may be familiar with still the ongoing debates in New Orleans, affected by Katrina, the big hurricane. And New Orleans was such a beautiful place before Katrina came. There's the French Quarter, the nice music, the jazz on the streets, and you could enjoy for days and days the great atmosphere in New Orleans. Suddenly, it was not that rich, by the way, but in any case, suddenly gone. For years, people left. But nowadays, if you go back to New Orleans, it's becoming again a great city. It has, okay, the whole inner city has been largely rebuilt in the old traditional atmosphere. The musicians are coming back and are back there, and gradually it's becoming a great tourist city. And people are coming back, so gradually they are back to where they started or they were at the beginning of Katrina. And there you have already one of the things we would say, well, yes, it has helped the city to rejuvenate itself. Now, every city, of course, as we know in the urban renewal movement, every city has to renew itself. Nothing can be stable forever. Architecture can be maintained, but a city is a dynamic organism, so it has to develop. So urban rejuvenation is a policy goal which is universally accepted. But you might say, if you get a shock, it might help a little bit, or maybe very much, an urban rejuvenation program. Even when you don't like the shock itself, but the long-run impacts, of course, could be very positive. So the research context, in fact, and that's a long-run research agenda in which we have been working for a couple of years now, and it's still continuing, is and taking natural disasters as an example. There are risks. Some of you may be familiar with the work of Ulrich Beck, the German quantitative sociologist, who has written his famous book on The Risk Society, where he articulates the different types of risks, and we have to manage risk. So risk management is one of the main challenges for modern governments. Nothing is certain, nothing is linear, nothing is completely predictable, but we have to manage risk. A big risk, of course, is a shock or a catastrophe. That's the biggest risk you can have. But if people are prepared, if governments and governance agencies are prepared, then, of course, at the end, they can cope with it and maybe improve their situation. And so you can have events and disasters, and then at the end, the right-hand side of this slide, you find different opportunities for economic growth, but also for social well-being. So the goal of this research agenda on new types of, let's say, uncertain, risky spatial dynamic phenomena is to find the impacts from a global perspective, not anecdotal, global perspective on cities or regions, urban areas, could even be countries, and then find out whether the blessing in disguise hypothesis, which is, mind you, is for the time being only a hypothesis. It could be falsified. Scientists has to be open to falsification. So maybe next year you will tell me you were wrong. Okay, then my hypothesis was wrong. That's not a scandal. It doesn't matter. So this is in fact part of the research agenda. Now the framework, because that's also why I started at the beginning by saying we can have many data. Later on we'll go to the database. You can have many data, but you need to have a conceptual framework and a little bit of a theory in order to test certain things. Otherwise, any hypothesis is vague and anything would do. And so what we have here is essentially what we have called the blessing in disguise, BID framework. It starts with an external shock, in this case, a natural disaster. It has, of course, an instantaneous effect. Look into the earthquake in Turkey, everything collapsed. Many people died, and so terrible disaster. But of course, you need to have a response. And you know that even during the recent elections in Turkey, the response mechanism in Turkey of Mr. Erdogan was heavily criticized because one of the complaints was, you didn't do anything. You just waited and nothing happened and people were suffering. So the instantaneous response set is important, but there also ought to be a strategic response set from which you have to choose. That is still missing, by the way, in Turkey. And that's also why there's still a lot of criticism despite the victory of Mr. Erdogan. How can we then build up a strategic response mechanism? And here you see the blue pentagon. The blue pentagon, here I refer to the work of my dear colleague, Roberto Czamanski, who passed away, unfortunately, a few months ago. But he was a great thinker. And one of his great ideas, through which he has become and has had a worldwide impact, is his view on the concept of territorial capital. And what is the view on territorial capital? If you want to, in fact, a rather simple view, but it's effective. If you want to achieve certain goals, then you create some sort of a production function of these goals. In this case, the goal is maximize HDI, so the Human Development Index. So that's the production function. And as factors in the production function, you have, in this case, would be more or less, but doesn't matter so much, 5 important capital categories. And Roberto Czamanski has spent a significant part of his life on the measurement of the effects of different types of territorial capital on regional well-being. He never worked on disasters, etc., but I think his conceptualization was very helpful and has helped me a lot to come to a better specification of analytical thinking on how to model statistically, econometrically, all these effects. So what is the territorial capital? That is human capital. Of course, that's a standard factor in any production function. Social capital, sometimes it happens in a production function like networking, community-based efforts, etc. Environmental resources, increasingly, especially in our Green Deal environment, put forward as an important factor also for regional well-being or national well-being. Productive capital, of course, that's quite clear because that's the standard neoclassical approach which we have adopted in economics, but also institutions. And institutions have been often the neglected factor in the analysis of productivity of nations and of the analysis of the growth of nations. But institutions have been always undersnowed in our analysis. Now, gradually, in more recent years, you also find it back in EU studies and ESPOM studies, etc. The quality of the institutional environment is increasingly seen as a major success factor. But you have to measure it, so that's the level. But we know this from many examples, how important it can be. Some of you may be familiar with the book of Menser Olsen, The Rise and Decline of Nations, and that was already in the 80s, I think, but I think in 1980s or so, but it's a beautiful book where already he gave the foundations for an institutional perspective on economic growth, but not modeled, just more reflective. But nowadays we can measure it much better. And in many recent articles, also published in various journals in the past years, we see lots of measurements of institutional quality. And that's a very important topic. An example, as a negative factor, as an indicator or proxy for institutional quality, we often use the degree of corruption in a country. And we have even worldwide corruption indices for all countries. So that is mapped out over many years. What is the degree of corruption? So it is a negative side of institutional quality as a proxy for institutional quality. So we have indeed also in this respect quite some indicators. Would institutional quality matter? A good example, Haiti. Haiti has been, of course, terribly affected by a severe earthquake. Port-au-Prince, but if you nowadays go to Port-au-Prince, the capital city, it's still a disaster. 13 years, I think, 13 years after the earthquake, it's still a disaster. And if you ask people, what is happening? Well, the government is, and they take the money because they got lots of money. The money was not the problem. The money was there, but the money was not either not spent or went into the wrong pockets. And of course, then nothing will happen. So institutional quality, solidity of governments, agencies, etc., is a major point. And that's why we had to introduce here in our Pentagon model institutional quality, because if you are in a recovery stage of a disaster, you need to have a solid, determined government. I would not always say that I would praise the Chinese government, but there's one thing we can also show later on in some figures. China is the country which is mostly affected by natural disasters. It has at least some 3 natural disasters every year. Did it ever affect China? Yes, it did, a little bit. But they know effectively how to respond in 1 year. If you come back after 1 year, problem solved, and all the recovery mechanisms have been put in place. So there are examples, and Japan is another good example. Earthquake in Kobe a few years back destroyed a significant part of the infrastructure, roads, and, harbor facilities, etc. But the Japanese also know how to handle earthquakes. So they are used to it and they have a mechanism to be put in place. One of the things, and that's also why I put a little bit more emphasis on the institutional quality, is that in Europe, we are happy, I can show you the figures, that we have very little natural disasters. Okay, the recent floods in northern Italy is an example of a natural disaster. And it was not always, I think, as far as I can see, given my own experience with natural disasters, not always very professionally handled, but it was handled in any way. But we do not have a system here in Europe where there's only one simple question. There's a big disaster. It can be a flood, earthquake, it can be a war, it can be anything, political unrest. First question in 10 seconds is, who is responsible? Who is in charge? What we do, we discuss. Is the mayor who is responsible? Is the governor who is responsible? Is the minister of interior who is responsible? Is the police who is responsible? Is the fireman responsible? If you discuss for hours who is responsible and no one agrees, then you are already too late. So one of the things we have learned, but also one of our advices to the government, make sure the competence question is clearly articulated before. And we have now we gradually in several countries, the same in Belgium and Germany, gradually different scales of disasters. And given a certain scale of disaster, then you know exactly who is responsible given the scale of disaster. And then you can, of course, effectively handle this Pentagon model, because then you know exactly what to do. There's short run, and there's, of course, also long run. So then you get here the capacity and capability thing, which is also based on works of Amartya Sen, Nobel laureate, who has indicated that in a production function, it's not only exactly
you push a button or you have an injection needle in your arm and the patient is recovered. No, you have the capacity to improve, but it's human intervention and human effort to improve the economic and well-being and performance. And so we have used also in the interpretation of our results, Amartya Sen's interpretation of the capability theory. And then, of course, you see the modeling effort going on, long run, socioeconomic impacts. We have GDP and well-being, etc. And at the end, you ask then the question, is there a blessing in disguise? Of course, I hope that maybe my proposition is correct, but it might be that it's not correct. That's why there's a question mark. So we have to critically evaluate the concept, theoretically, conceptually, empirically, and also from a statistical econometric perspective. Just very quickly then on some of the data. Okay, I'll speed up. I could talk for hours, but and the data, I think, are interesting in the sense that there are quite a few databases on natural disasters. Even we have databases for more than 100 years documented on disasters, but certainly in the last 20, 25 years, we got very specific databases on the type of disaster, where it happened, how many people affected, how many people killed, how many houses destroyed, and the estimate damage cost. Of course, it could always be a little bit vague. That's what we know. Of course, there's quite some uncertainty in all these cost assessments, but at least we have an idea on the order of magnitude of all these disasters. So we have used all these, the whole range of different data systems. You can also find them in the article, which I have just shown, and it continues, etc. Now here you have over an X number of years starting up to now, the different types of disasters in different parts of the world, etc., and income groups affected of people and so on. So this is a rather well-known documentation. Once you have all these data put in place, here you have then the measurement, the operational measurement of the HDI index, and then you can try to find out what is happening in the short run, what was happening in the medium term, what was happening in the long run up to 50 years, depending on the database we had. So sometimes 25 years, and that has been a rather extensive data exercise. Here you find some sort of a correlation analysis between the different data on the vertical and horizontal axis, and you can look into the question whether there is a close correlation between some of these data. And of course, in many cases, there is some correlation between all of these data. That is quite evident, which is not a scandal because there's reality. But then, of course, you can do all kinds of cluster analysis to find out, can we identify clusters of disasters and clusters of countries or regions which have been equally affected and so on. And based on that cluster analysis, of course, you can then see, can we categorize certain types of disasters which are more beneficial than other types of disasters in different parts of the world. Well, okay, I'll just go quickly because I know I have to, and I have here we have the results of the PUP. Yeah, I go immediately then to the conclusions because I could talk for hours on the econometrics and the statistics, but we want to have a reflection on the type of models which we could use, and that brings us to the type of conclusions which we tentatively have been reaching. So first, empirically. So it's evidence-based. Crisis can shape new perspectives. And in many cases, they do. That's the second bullet point. Disasters, in many cases, sustain the hypothesis of blessing in disguise. If there is not a blessing in disguise, then it turns out that especially physical geography can play a role, because if you're in a mountainous area, it's very difficult, of course, to go for a recovery program. But especially, of course, the quality of institutions is a critical factor, more important than
international financial aid by the World Bank or IMF or whatever. Much more important, how people feel about it, and can we stand up and make the best out of a disaster. In fact, just on a personal note, that's also what I have found in the past year when I was a couple of times in Ukraine. Despite all the disaster, but people were standing up. I mean, we have been developing plans in bomb shelters where we could not go outside for a day, but people were thinking on, we want to improve and we want to have a better society. So that is the type of, despite all the also the institutional weaknesses in Ukraine, which also ought to be admitted, but there is a spirit, and that spirit, I think, is good for the blessing in disguise. So at the end of the day, what I would say is this hypothesis on spatial dynamics and recovery after a shock, in fact, is nothing else than a Schumpeterian view on society and on the economy. Schumpeter then would say, well, you have to sometimes to destroy certain things in order to improve. In this case, you do not deliberately destroy things, but it has happened. But in a way, my positive view is, at the end of my story, positively inspired by good old Joseph Schumpeter. So having said this, I stop here. Thank you.
Thank you, Peter. If my colleague can join me, so if I have any question or comment, I will have a lot of questions, but I only noticed that in parabola you show when you reach the minimum, there is no time scale. So you see, it's easy to destroy a city. I mean, you can bomb it for 2 days, or an earthquake, it takes few hours, but to reconstruct, it takes 50 years. So that's a big difference, but this is also a very silly comment. I leave the floor to Professor.
Yes.
Silvia.
Well, thank you very much for your interesting presentation. I really enjoyed the presentation and also reading your paper and also other papers you and other colleagues wrote on this topic. But before, yes, there is a question for the floor, and then I don't know whether we have also some other questions from.
Still not.
Not yet.
Not until now.
So thanks for the talk. And I try to guess to give some example in order to see if we agree or not. So we are becoming older. This is the fact. And one explanation is that our immune system is changing. And how it's changing? Because we get disease and our immune system react to the disease and become stronger and stronger. Because as we get more and more disease, that is some shock, our immune system learn about the virus, about the disease, so the next time you get no more. But what is the problem? Is that the space is finite. So at a certain moment, we have no space to learn more. So we have no recovery. There is some irreversibility in the system. And this is a possible explanation why we become older and at a certain moment we die. So in some sense, I could agree in principle that shock could be good if, for example, you are younger and you get a disease and then you get stronger. And this is why, for example, the European people can colonize all the world, because we are very prepared to have a virus. We have a lot of invasions. But finally, there is this irreversibility process in our biology, but I think also in the world, that some process can be reversed. You can reconstruct, you can come back. If you destroy the Amazon forest, you cannot reconstruct Amazon forest. It's not possible. This is like an unstable equilibrium. So if something happened there, we cannot recover. So how you can concile your abstraction with this irreversibility that we observe in many systems?
Well, thank you very much. I like your medical metaphor, but the good news is that cities or regions or countries are not human bodies. The human body is subject to certain laws of biology, etc. And even when you have the best immunity system, At the end of the day, you will, after a disease, not become more healthy in most of the cases. You might be lucky enough to get back to the original level of health. But human societies have one more thing compared to a biological organism, and that is they have brains, and the brains can help them to improve the economy, the society, the city, the region, the business in which they are working, even when they are hit by a shock. And one of the things which I did not yet mention, that's a follow-up research which I have recently also started, is the following, based on a statement of Albert Einstein. Albert Einstein has said, smart people are able to cope with catastrophes, but intellectual people are able to prevent them. So it's not only coping with a disaster once it's there, the main question is, can we build up prevention mechanisms? And that is, I think, that will be also in terms of proactive governance. That will be the main challenge. I give you one example from my own country. You see, the Netherlands, Low Countries, near the sea. As an anecdote, my house is 5 meters below the sea level, and I'm close to the sea. So if a dike breaks, you can all pray for me, but it doesn't help anymore. It's too late. So what we do is, of course, we build up preventive mechanisms. We invest billions and billions every year on dike protection, on water management, on all things. And there is never a dispute on whether the money is well spent. Everyone recognizes. If we just start to discuss democratically what should be done, we discuss forever, but we are lost. So no discussion, you just do it. Nowadays, very much digitalized, everything is computers controlled, etc. Every square meter is controlled, because we know we do not invest in all these equipments as a preventive mechanism. Also with sea level rise, in 50 years, we will not exist anymore. So that is an important element. And as part of our research agenda, to follow up on what you said, we are now starting a new project on not only the recovery mechanism, but also on the prevention mechanism. Because you see, the political argument is very often, should we invest in preventing certain things, whether it's on traffic accidents or on airline safety, is it worth? And because you can only spend public money only once, and then it's gone. So if you make a mistake, you are lost. But we have tried to, for 40 cities in the world, all over the world, 40 major cities, to look into the annual budgets by cities in terms of preventive expenditures. And then you might ask again the empirical question. If we spend a lot of public money on prevention mechanisms, all kinds of things, could be dike protection, but it can be safety, it can be police, it can be firemen, it doesn't matter. It's not unproductive, as many people and sometimes politicians argue. It is not productive. We like production is we produce goods, but we produce safety. And that is the point. The tentative findings we have now is that these 40 cities, in almost all cases, except in a few cases in the developing world, but in almost all cases, those cities which invest heavily also in preventive mechanisms, as far as we can distill it from public budgets and so on, that these cities also perform economically and socially very well. So based again on empirical facts, because empiricists at the end of the day, based on empirical facts, I think we could formulate soon a second hypothesis also on coping with threats. In fact, that was the statement by Albert Einstein. Yeah? Intellectuals can prevent disasters. I think that could be the second hypothesis, which we also might soon be able to test.
Thank you very much. I think what you said now is very important because prevention is the first thing to do. Otherwise, one might think that, you know, a disaster is a blessing, which I mean, different is saying that when it happens, of course, it's better if you try to turn a crisis into opportunities, of course. And so I really think that this idea of blessing in disguise is very promising and very useful for countries to react to shock and to be able to go back not to the previous equilibrium, but to reach a new equilibrium with a better quality of life for the affected population. But of course, prevention is important because we wouldn't like to have disaster. And as in the question you put before, is not just a problem of the symmetry with the human body, but it was also talking about some irreversibility, for example, talking about the forest, the Amazonian forest. If you destroy the Amazonian forest, you don't, in 10 years, you will not have a new Amazonian forest, and all the world will be affected. So there is a problem of irreversibility also in our world, in the society. And of course, we have to prevent huge disaster from which you cannot recover in 10 or even in 20 or even in 100 years. But I know that there is a question from Roberto, so I stop here.
Maybe Peter, you already kind of partially answered my question, but I would like to pick up on the word that Mirko mentioned, which is time. Now, recovery happens over time, of course. And, you know, when you have, let's say, extremely rare events like a war in developed countries, an extremely rare event, an earthquake, you might say it's a rare event. And so you have plenty of time to recover. But what we are learning now is that when it comes in particular to, let's say, extreme meteorological events, floodings, etc., they're not necessarily stronger than they used to be in the St. Catherine flood, but they're more frequent. That leaves you less time for recovery until the next one hits in the same place, right? The probability of being hit again is higher with climate change becoming stronger. So I was wondering if you factored in somehow in the rest of the study that, unfortunately, yet to speed up on the factor of time for recovery. And of course, I guess prevention is part of your answer. Yeah.
Thank you, Roberto. A footnote compared to what you said. I started my presentation with the St. Elizabeth flood in 1421. In 1416 and in 1423, 3 times in a row, a major flood. The one I mentioned was the worst, but there was a major flood before, and there was 2 years later, again, another flood. So the frequency was very high. I think compared to what we have seen from normal meteorological data. But I think what is important is not the frequency, but it's the predictability. The predictability of the events is, in my view, is the main problem. And of course, with current climate change, we know there have been floods before in northern Italy. There have been floods all over the world. There have been all kinds of disasters. But the fluctuations which we are observing nowadays are much higher than before. And a drought, give an example, in Africa, in many countries, is a very stable thing. So you would not say it's a frequent thing. It is very stable for many years. But nevertheless, we cannot predict it very well. So our models are insufficient so as to provide, for the time being at least, sufficient support for effective public and policy intervention. And I can only tell one thing, and I'm here in an academic environment, but I mean what I say. One of the most effective preventive public expenditures is education and research. Let's not forget that. Knowledge is the key to coping with all kinds of disasters, challenges, and also new opportunities. So the only plea I have also in this university environment, let's not forget to invest heavily in new scientific knowledge. And there can never be enough investments in knowledge.
Yeah, right, completely right. Thank you very much. I don't know whether there is some other question from the floor or from online. So can do I have time, Mirko, to make a question or not?
The last one.
The last one. Okay, two related questions. So no. I mean, reading well from your presentation and also from your paper, it is clear that in order to have this ability to bounce forward, it is to have good institutions. You said it before, no? There are several drivers which are important, but one of these, and you underline this, is institution, which means good government, able to have a long-term vision, long-term perspective, efficient bureaucracy, able to coordinate at different levels of governments, able to cooperate with stakeholders on the territory, and so on and so forth. So it's not just a matter of not having corruption, as you said, or a right allocation of responsibilities, which is, of course, very important, but is not sufficient. As far as I understood, you need also an efficient bureaucracy, a good government, long-term perspective, and so on and so forth. Unfortunately, I am, a public finance economist, so I'm very keen on public policy, and public failures are very frequent. Most of the time, governments are short-minded. The politicians are short-minded because they think the next election, and bureaucracy is not so efficient as we would like to be. They could be, and so how would you think we could, as a researcher, help to overcome these public failures? And if I have the time, yes. A related question, which goes from the public to the private sector. As we know, in the private sector, an increasing number of companies, in particular large companies and listed companies, are increasingly forced to follow ESG targets, environment, social, governance. And I mean, I think what is happening is very important, because companies, now it's compulsory for big companies and listed companies, but in the value chain, of course, this issue will interest more and more often also the small and medium companies. And the EU is also working in order to enlarge the number of companies who are forced to state precise ESG target. So companies have to measure the impact that they have on social and environment, and they also have to do the reverse, because they have to take into account how the climate change, for example, of the demographic change will affect their business. So it's a matter of long-term sustainability. And I think that the system started working. So the question is, do you think this development is important and could have an important role to be able to move in this direction of transformative resilience, blessing in disguise, and so on and so forth? And do you think that adopting something similar to the public sector could help to overcome, to reduce the public failure I was talking before? Thank you.
Well, thank you very much. You challenged me. I'm just hoping to finish over the summer period a new book on what is called decoding cities. And one of the questions I have asked there myself is an old question by Kevin Lynch, one of the old British urbanists. The question was, what is a good city? And that has prompted a lot of research. What is a good city? Define what is a good city, and in a measurable sense. Otherwise, it doesn't help. Lots of discussion, not a clear solution. In fact, at the Quito declaration, the conference in Quito on the SDGs, so the Sustainable Development Goals, an attempt has been made to, in a more quantitative, measurable, transparent sense, to define what could be a good city, or in general Sustainable Development Goals, but you can apply this to cities in the new urban agenda. So there have been some attempts. One question still remains, and now you challenge me, which I like. I could ask the question, what is a good city government? And no one has ever discussed this. And if I would have a wish, and maybe we can work on it, I would like to specify some, maybe 17 or more or less than 17 SDGs for city government, not for cities. That's what we know in the meantime. We can measure it. The HDI exercise we have used was there. But can we, through a new system, measuring SDGs for city governments, then I think we could have some sort of a measurable scheme which we could use as a learning mechanism worldwide. I think that could mean a breakthrough. So I'm in to think about it.
There are no other questions, maybe given the timetable.
If you agree, we should thank the speaker again, and then I would like to give the floor to Professor Roberto Scazzieri, that it will have a final contribution and concluding remark. Aura, would you like to join us also, please? So we are going to the conclusion and the final part of this meeting. Thank you very much.
Well, yes, so I'm supposed to substitute Professor Paola Monari in this function. The final speaker was supposed to be Professor Alberto Quadrio-Curzio, fellow of this academy and President Emeritus of the National Lincei Academy. Unfortunately, for a concomitant meeting at his own home university, could not attend today's meeting, but he sent us a short set of remarks, asking me to read this set of remarks on his behalf. He wrote, I'm pleased to open the final session of this workshop on entropy, complexity, and spatial dynamics at the Accademia delle Scienze dell'Istituto di Bologna, and I'm grateful to Professors Aura Reggiani and Roberto Scazzieri, fellows of the Bologna Academy and coordinators of this workshop, for inviting me to do so. The objective of the workshop was to elicit an interdisciplinary discussion on the themes considered in the Handbook, Entropy, Complexity, and Spatial Dynamics, a rebirth of theory, ? The subtitle of the handbook is A Rebirth of Theory, ? And I would like to briefly reflect on the theme that this subtitle suggests. Let me start with the consideration that the question mark at the end of the subtitle would have been unnecessary until a few years ago. For the close interdependence between theory and evidence has been a landmark of scientific progress since the scientific revolution of the 17th century, which allowed enormous cognitive progress thanks to its ability to overcome the cleavage between theoretical construction and the manipulation of objects that was the hallmark of most previous attempts at investigating the nature of reality. Recent developments, ranging from the big data revolution to certain aspects of artificial intelligence have made it possible to doubt the continuing role of theory for the progress of human learning. I would like to forcefully stress that scientific progress without theoretical understanding is impossible. Indeed, both the big data revolution and artificial intelligence make theoretical understanding more necessary than ever. This is primarily because of the nature of the complex systems that have been the object of this workshop. As the Nobel economist Herbert Simon pointed out in his paper on the architecture of complexity, complex systems at advanced stages of organization are characterized by hierarchical structures. But these structures may be differently visualized depending on which point of view is adopted. This feature of organized complexity makes the description of such complex systems a fundamental step in understanding their properties. As Simon pointed out, the selection of a right description of interdependencies is a necessary condition for identifying the laws governing their structure and their possible dynamics. Smith's view is fully consistent with the so-called theory dependence of observations, which has been widely discussed in philosophy of science. This handbook and the discussions that it will stimulate would be an important and invaluable contribution to the progress of knowledge in the socio-economic sphere. This is the end of Professor Quadriocurcio's remarks, which I think are, if I may add something to that, are very closely in line with what we have been discussing and trying to build upon during this afternoon's workshop. I think that perhaps we should open the floor if there are any further general remarks or questions concerning the overall set of themes we've been discussing today. If either from people attending the workshop in presence or from people attending the workshop from remote. If not, I think I would I am extremely pleased to give the floor to Professor Reggiani, who I think perhaps would like to give us some final remarks and also perspectives for further work.
Yeah, so I would like to thank everybody because it was really a rich afternoon. And then I think we need more time for meditating, for discussing, and for going on to go ahead in future research direction. And then I would like, in fact, maybe to talk again to all of you, maybe in 1 year, would be nice to meet again, because we started with the dynamics, with evolution, with complexity, we finished with resilience. I think that there are still topics to examine. For instance, the network resilience, the role of connectivity, the role of accessibility in all the arguments that we have approached, and from both the theoretical and applied and policy viewpoint. So we have seen, Professor Bhatti, several similarities in the laws. So, and then mostly we have seen simple law for mapping out the complex environment. So also the spatial interaction, the rank size, and so on. So there are still old challenges to solve, and there are new challenges that we started to face. And I would like to go on with these old and new challenges. So I would like to invite all of you again in a next meeting. So I hope that the Academy, maybe we lost the new one, maybe now we forget the book, we go on with new ideas. Peter says creative distraction, and then we go on for the future with really new ideas and so on. So I really would like to thank, and I would like to thank the chair and Professor Scazzieri and the Academy and all of you, and of course the colleagues and friends that are following us from the United States, from Europe, from all over the world. I really thank them a lot. And I hope them to see them, meet them physically and virtually again. So Mirko, if you want to close.
No, I just want to thank you and all the organizer, all the editor and the author for this handbook. And let me thanks again the speaker which gave this great contribution. Thank you very much to all of you.